Welcome to our exploration of high-density polyethylene, that remarkable material that quietly serves us in countless ways throughout our daily lives. Tonight, we begin our journey into the molecular world of HDPE, examining the fundamental characteristics that make this polymer so uniquely suited to its many applications, from the humble milk jug to industrial containers and beyond. Let us start at the very heart of what makes HDPE what it is: its molecular weight. When we speak of molecular weight in the context of high-density polyethylene, we are referring to a range that typically spans from 100,000 to 500,000 grams per mole. This number might seem abstract at first, but it holds profound significance for the material's behavior. The molecular weight dictates the length of the polymer chains themselves, determining how these long, thread-like molecules will interact with one another, and how they will respond when heated to their melting point. A chain with a molecular weight near the lower end of this range, around 100,000 grams per mole, will be relatively shorter, while a chain approaching 500,000 grams per mole stretches considerably longer through the molecular landscape. This range of molecular weights gives manufacturers the flexibility to fine-tune the properties of HDPE for specific applications, balancing processability with performance characteristics. The longer chains generally provide greater strength and toughness, while shorter chains may offer easier processing during manufacturing. As we contemplate these molecular chains, it becomes essential to understand their structure, their architecture at the most fundamental level. High-density polyethylene distinguishes itself through an elegant simplicity in its molecular form. Unlike its cousin, low-density polyethylene, HDPE exhibits minimal branching along its carbon backbone. To be more precise, HDPE contains less than one side chain per 100 carbon atoms. Imagine a long highway stretching across a vast landscape, with only the occasional side road branching off here and there. This is the molecular geography of HDPE. Each carbon atom along the main chain bonds to the next, creating a nearly linear pathway. This minimal branching is not merely a structural curiosity. It is the key to HDPE's density and strength. When polymer chains lack extensive branching, they can align themselves parallel to one another, nestling together like logs stacked neatly in a pile. This efficient packing is what gives high-density polyethylene its name and its character. The branches that do exist are brief interruptions in an otherwise orderly structure, and their rarity ensures that the overall linearity of the chains remains intact. This linear structure leads us directly to one of HDPE's most important characteristics: its crystallinity. When we speak of crystallinity in polymers, we are describing the degree to which the molecular chains organize themselves into ordered, repeating structures, much like the regular lattice of atoms in a mineral crystal. High-density polyethylene typically exhibits crystallinity between 60 and 80%. This means that more than half, and often as much as 4/5, of the material consists of regions where the chains have arranged themselves in precise, parallel alignment. These crystalline regions form during cooling as the polymer solidifies from its molten state. The linear chains, unencumbered by excessive branching, slide alongside one another and lock into position, creating zones of molecular order interspersed with amorphous regions where the chains remain in a more random, tangled configuration. This high degree of crystallinity contributes significantly to HDPE's stiffness, its opacity, and its resistance to chemical penetration. The crystalline domains act as physical crosslinks, anchoring the material and preventing the chains from sliding past one another too easily under stress. The consequences of this molecular architecture extend to the forces that hold HDPE together. The linear chains of high-density polyethylene generate intermolecular forces that are roughly 1.8 times stronger than those found in branched low-density polyethylene. These intermolecular forces, primarily van der Waals interactions between the closely packed chains, arise from the temporary fluctuations in electron distribution along the carbon backbone. When chains lie parallel and close together, as they do in HDP, these weak forces accumulate and multiply across the length of the molecules, creating a cumulative binding effect that is quite substantial. In low-density polyethylene, the numerous branches prevent the chains from approaching one another as closely, reducing the effectiveness of these intermolecular attractions. The result is that HDP, with its nearly branch-free structure, achieves a significantly stronger network of molecular connections. This enhanced intermolecular bonding translates directly into practical properties: higher tensile strength, greater resistance to deformation, and improved barrier characteristics against liquids and gases. Now, let us turn our attention to how this remarkable material comes into being. The creation of high-density polyethylene requires special catalysts that guide the polymerization process with precision. One of the earliest and still widely used approaches involves activated chromium oxide catalysts, which enable what is known as slurry polymerization. In this process, ethylene gas is introduced into a liquid medium containing the chromium-based catalyst. The catalyst, carefully prepared and activated, encourages ethylene molecules to link together, forming the long chains characteristic of HDP, while simultaneously suppressing the formation of branches. The chromium oxide sits on a support material, providing numerous active sites where polymerization can occur. As chains grow from these sites, the catalyst's geometry and chemical nature ensure that branching remains minimal, preserving the linear structure essential to high-density polyethylene. The slurry process allows for excellent heat removal and produces HDP with consistent properties, making it a foundational technique in the industry. Building upon this foundation, scientists and engineers have developed even more sophisticated catalysts. Ziegler-Natta catalysts represent a major advancement in HDP production, offering the ability to tailor molecular properties specifically for applications such as bottle-grade resins. These catalysts, typically based on titanium compounds combined with aluminum co-catalysts, provide exceptional control over the polymerization process. By adjusting the catalyst composition, temperature, pressure, and other reaction conditions, manufacturers can target specific molecular weight distributions and crystallinity levels ideal for blow molding bottles. The Ziegler-Natta system produces HDP with just the right balance of flowability for processing and strength for performance. A milk jug manufactured from Ziegler-Natta catalyzed HDP exhibits the stiffness needed to hold a gallon of liquid while maintaining enough toughness to resist cracking if dropped. The catalyst's ability to fine-tune these properties has made it indispensable in the production of container-grade HDP. The evolution of catalyst technology continued with the development of metallocene catalysts, representing yet another leap forward in precision polymerization. Metallocene catalysts feature a distinctive molecular structure, often described as resembling a sandwich, with a metal atom held between two organic ring structures. This precise geometry creates extraordinarily uniform active sites for polymerization. Unlike earlier catalysts that produce a relatively broad distribution of chain lengths, metallocene catalysts generate HDP with much narrower molecular weight distributions. This means that the chains in metallocene catalyzed HDP are more similar to one another in length, creating a more homogeneous material. The uniformity translates into more predictable processing behavior and more consistent final properties. While metallocene catalyzed HDP may come at a higher cost, its superior uniformity makes it valuable for applications demanding the tightest tolerances and most reliable performance. When high-density polyethylene first emerges from the polymerization process, it possesses a characteristic appearance that reflects its internal structure. Raw HDP appears cloudy, almost milky in its translucence. This cloudiness arises from the way light interacts with the material's crystalline domains. As light passes through HDP, it encounters boundaries between crystalline and amorphous regions. These boundaries, where ordered molecular arrays transition to disordered tangles, have slightly different optical properties. The difference in refractive index between crystalline and amorphous zones causes light to scatter in many directions, rather than passing straight through. This scattering is what creates the cloudy, opaque appearance of HDP. The higher the crystallinity, the more pronounced this scattering effect becomes. A milk jug's familiar white appearance owes itself to this light scattering phenomenon, with billions of tiny crystalline domains diffusing light in all directions. To transform raw HDP into a form suitable for manufacturing, the material undergoes a process called pelletizing. In this process, the polymer is melted and reformed into small, uniform pellets or granules. The melting breaks down the original crystalline structure that formed during polymerization, converting the solid polymer into a viscous liquid where chains can move freely. This molten material is then extruded through small openings and cut into pellet form as it cools. The pellets, typically a few millimeters in size, provide a uniform, easy-to-handle form of the resin. These pellets can be readily metered into processing equipment, mixed with additives if needed, and stored or transported efficiently. When the pellets are later melted again during blow molding, injection molding, or other forming processes, the chains once more transition from their crystalline arrangement to a flowing melt, ready to be shaped into the final product. Upon cooling in the mold, crystallinity redevelops, locking the chains into the desired form. Finally, it is worth noting that the processing conditions used in manufacturing can significantly influence HDP's final crystallinity. Under carefully controlled circumstances, crystallinity can be tuned to reach levels as high as 90%. Achieving such elevated crystallinity typically requires slow, controlled cooling that gives chains maximum time to find their most ordered arrangement. The temperature profile during cooling, the pressure applied, and even the presence of nucleating agents can all influence how extensively the chains crystallize. Higher crystallinity brings increased rigidity, as more of the material consists of those tightly packed, ordered regions that resist deformation. An HDP product with 90% crystallinity would be exceptionally stiff and strong, though potentially more brittle than material with lower crystallinity. The ability to adjust crystallinity through processing gives manufacturers another tool for optimizing HDP performance, balancing stiffness against toughness, rigidity against flexibility, to create materials perfectly suited to their intended applications. As we conclude this first segment of our journey through the molecular landscape of high-density polyethylene, we have established the foundational understanding of this remarkable material. We have seen how molecular weight determines chain length, how minimal branching enables tight packing, how crystallinity creates strength and opacity, how intermolecular forces bind the structure together, and how various catalysts guide the formation of these precisely engineered chains. We have witnessed the cloudy appearance of raw HDP and understood its origin in light scattering, observed the pelletizing process that renders the material processable, and recognized how processing conditions can fine-tune crystallinity to achieve desired properties. These fundamental principles form the bedrock upon which all of HDP's remarkable properties rest, the molecular foundation of the milk jug, and countless other applications that depend on this versatile polymer. Having established the molecular foundation of high-density polyethylene in our previous segment, we now turn our attention to the mechanical properties that emerge from this carefully structured material. These properties, strength, flexibility, hardness, and toughness, are not abstract specifications, but rather the tangible manifestations of those tightly packed, linear molecular chains working in concert. Tonight, We explore how HDPE translates its molecular architecture into the remarkable performance characteristics that make it indispensable for containing, protecting, and transporting the substances we use every day. Let us begin with tensile strength, one of the most fundamental measures of a material's ability to resist being pulled apart. High-density polyethylene exhibits a tensile strength ranging from 26 to 33 megapascals. To understand what this means, we must first appreciate the megapascal as a unit of pressure or stress. 1 megapascal represents 1 million pascals, or 1 million newtons of force distributed across 1 square meter. When we say HDPE has a tensile strength of 26 to 33 megapascals, we are saying that a sample of this material can withstand that magnitude of pulling force before it begins to yield or break. This range of values reflects variations in crystallinity, molecular weight, and processing conditions. An HDPE resin at the higher end of the crystallinity spectrum, with longer chain lengths and more perfect crystalline domains, will approach the upper limit of this range. What makes this tensile strength particularly remarkable is the context of HDPE's density. This material achieves exceptional strength relative to its weight, offering a strength-to-weight ratio that few materials can match. The linear chains, aligned and packed closely together, distribute tensile loads efficiently along their length, engaging the strong carbon-carbon bonds of the polymer backbone and the cumulative van der Waals forces between adjacent chains. This brings us naturally to consider the density of high-density polyethylene itself, which ranges from 0.941 to 0.965 grams per cubic centimeter. This relatively low density, lower than water, which sits at 1 gram per cubic centimeter, is what allows HDPE containers to remain lightweight even as they provide substantial strength. The density arises from the mass of the carbon and hydrogen atoms that compose the polymer chains and the efficiency with which those chains pack together in three-dimensional space. The crystalline regions, where chains align in order to raise, pack more efficiently and contribute to higher density within that range. The amorphous regions, where chains remain tangled and disordered, pack less efficiently and would, if isolated, exhibit lower density. The overall density of an HDPE sample represents the weighted average of these crystalline and amorphous components. That HDPE achieves its impressive mechanical properties while maintaining such low density is a testament to the efficiency of its molecular design. The material needs no heavy metal reinforcement, no dense mineral fillers, just carbon and hydrogen arranged with precision. Consider, for a moment, the practical implications of this strength-to-weight ratio. A typical high-density polyethylene milk jug weighs approximately 60 grams, just over 2 ounces. This small mass of polymer, properly shaped and formed, can safely carry over 1 gallon of liquid. 1 gallon of milk weighs approximately 8.6 pounds, or roughly 3.9 kilograms. The jug must not only contain this weight, but also withstand the dynamic forces of being lifted, carried, tilted, and set down repeatedly. The 60-gram HDPE structure achieves this through the intelligent distribution of material in its walls, handle, and base, combined with the inherent strength of those tightly packed polymer chains. Each square centimeter of the jug's wall, just a fraction of a millimeter thick, bears its share of the load, with the molecular chains oriented and aligned to resist the stresses imposed. The jug's form follows from its function, and both are enabled by HDPE's remarkable strength-to-weight characteristics. It is a quiet marvel of materials engineering that we encounter daily without a second thought. Beyond tensile strength, we must consider how HDPE resists bending, a property quantified by its flexural modulus. High-density polyethylene exhibits a flexural modulus ranging from 800 to 1,400 megapascals. The flexural modulus measures a material's stiffness when subjected to bending forces. Essentially, how much a beam of the material will deflect under a given load. A higher flexural modulus indicates greater resistance to bending. For HDPE containers, this property becomes crucial when bottles and jugs are stacked during storage and transportation. Imagine a pallet loaded with dozens of milk jugs, each weighing 9 or 10 pounds when filled. The jugs on the bottom tiers must support the weight of all those above without buckling or deforming excessively. The flexural modulus of HDPE ensures that the jug walls maintain their shape under these stacking loads, preventing collapse that could compromise the integrity of the containers or the stability of the pallet. The crystalline regions within the HDPE contribute significantly to this stiffness, acting as rigid domains that resist the chain movements associated with bending. The higher the crystallinity, the higher the flexural modulus tends to be, as more of the material consists of these stiff, ordered zones. Closely related to flexural properties is compressive strength, which measures how well a material withstands forces that attempt to squeeze or crush it. High-density polyethylene demonstrates a compressive strength of 20 to 28 megapascals. When milk jugs or other HDPE containers are stored in palletized configurations, as they almost invariably are in warehouses and during transport, the containers experience significant compressive loads. The weight of upper layers presses down on lower layers, creating compression in the jug walls and bases. HDPE's compressive strength ensures that these containers can endure such loads without permanent deformation or structural failure. The chains within the material resist being pushed closer together, as the crystalline domains and intermolecular forces work to maintain the material's volume and shape. A jug that could not withstand palletized storage would be of little practical use in modern distribution systems, where efficiency demands that products be stacked high and transported in bulk. HDPE's compressive strength, combined with its flexural modulus, makes such logistics possible. Another important mechanical property is hardness, specifically measured on the Shaw-D scale for rigid plastics like HDPE. High-density polyethylene typically exhibits a Shaw-D hardness of 60 to 70. Hardness measures a material's resistance to surface penetration or indentation. In practical terms, how difficult it is to scratch, dent, or abrade the surface. The Shaw-D test uses a specific indenter shape and force, measuring how deeply it penetrates the material. A Shaw-D value of 60 to 70 places HDPE in the semi-rigid category, hard enough to resist scratching and abrasion during handling and transport, yet not so hard that it becomes brittle. During shipping, milk jugs and other HDPE containers inevitably experience rough treatment. They slide against each other, rub against packaging materials, and encounter various surfaces. The material's hardness helps preserve the integrity of the container walls and maintains the aesthetic appearance of the product. Excessive scratching could compromise both the structural integrity and the consumer appeal of the packaging. The hardness of HDPE arises from the same tight packing of chains that generates its other mechanical properties, with the crystalline regions again playing a central role in resisting surface indentation. At the atomic level, the semi-rigid character of HDPE and its resistance to buckling can be traced to the close packing of carbon and hydrogen atoms within the polymer structure. Each carbon atom along the polymer backbone bonds to two other carbon atoms in the chain and to two hydrogen atoms projecting from the chain. This tetrahedral bonding geometry, characteristic of saturated hydrocarbons, creates a structure where atoms are held at specific distances and angles by the strong covalent bonds. In the crystalline regions of HDPE, these chains align parallel to one another, and the hydrogen atoms of one chain nestle into the spaces between hydrogen atoms of neighboring chains. This efficient packing maximizes the van der Waals interactions between chains while minimizing empty space within the material. The result is a dense, cohesive structure that resists buckling. The the sudden, catastrophic bending or collapse that can occur when compressive loads overwhelm a structure's ability to maintain its shape. The regular geometry of the polymer chains and their efficient packing create a material that can bear loads stably, deflecting gradually and predictably rather than failing suddenly. One of the more elegant features of HDPE containers is the integrated handle, found on most milk jugs and many other bottles. These handles are not separate pieces attached after molding. Rather, they are molded from continuous polymer chains in a single operation. During blow molding, the molten HDPE expands to fill the mold cavity, including the void that will become the handle. The material flows and fuses together, creating a seamless structure where the handle is molecularly continuous with the body of the jug. This integration eliminates the weak seams that would exist if the handle were attached separately through welding or adhesive bonding. The polymer chains extend continuously from the jug wall into the handle and back again, ensuring that the handle can bear the full weight of the container without risk of separation at a joint. When you lift a gallon of milk by its handle, you are relying on this molecular continuity. There is no interface, no bond line, just one uninterrupted network of polymer chains distributing the load. This seamless construction is possible only because HDPE can be processed in its molten state and will resolidify with full structural integrity. The geometry of HDPE containers also plays a role in their performance, with square jug designs being particularly common for milk and other beverages. The square shape is not merely aesthetic. It leverages the uniform chain packing of HDPE to create flat, stable bases that resist tipping and allow efficient use of shelf and pallet space. When HDPE cools in a square-bottomed mold, the chains align and crystallize in a way that creates uniform strength across the flat surfaces. The corners of a square jug can be reinforced during design to handle the concentrated stresses that occur there, while the flat walls provide maximum volume within a given footprint. Square jugs stack more efficiently than round ones, wasting less space during storage and transport. The flat base makes the container stable on shelves and reduces the risk of tipping. HDPE's ability to form precise, consistent shapes during molding enables these geometric optimizations, with the material's uniform properties ensuring that flat walls remain flat and corners remain sharp even under load. Finally, we must consider impact resistance, one of HDPE's most valuable characteristics. The polymer chains in HDPE possess the ability to absorb impact energy without undergoing brittle fracture. When an HDPE container is dropped or struck, the impact delivers energy rapidly to a localized area. In a brittle material, this energy would propagate as a crack, causing catastrophic failure. In HDPE, however, the long polymer chains can disentangle slightly, stretch, and deform, absorbing the impact energy through these molecular movements. The amorphous regions, where chains are already in a disordered state, can accommodate this deformation most readily, acting as shock absorbers between the more rigid crystalline domains. The result is that HDPE containers can withstand significant impacts. A dropped milk jug typically bounces rather than shatters, perhaps denting slightly, but maintaining its integrity. This toughness is essential for consumer packaging, where rough handling is inevitable. The molecular basis of this impact resistance lies in the length and flexibility of the polymer chains, their ability to slide past one another to a limited degree, and the semi-crystalline structure that balances rigidity with toughness. As we conclude this second segment of our exploration, we have witnessed how the molecular architecture of high-density polyethylene translates into a comprehensive suite of mechanical properties. We have seen tensile strength that provides exceptional load-bearing capacity relative to weight, low density that keeps containers lightweight and economical, the remarkable efficiency of a 60-gram jug carrying a gallon of liquid, flexural modulus that prevents deformation under stacking, compressive strength that enables palletized storage, hardness that resists abrasion during transport, atomic packing that creates semi-rigid buckling resistance, integrated handles molded from continuous chains without weak seams, geometric designs that leverage uniform material properties, and impact resistance that prevents brittle fracture. These properties, working together, create a material uniquely suited to the demanding requirements of modern packaging and countless other applications where strength, lightness, and durability must coexist. As we continue our journey through the world of high-density polyethylene, we now shift our focus from the static mechanical properties we explored in the previous segment to the dynamic performance characteristics that govern how HDPE behaves in real-world conditions. A material may possess impressive strength in laboratory tests, but its true value emerges in how it performs across temperature extremes, under repeated use, in the presence of moisture and chemicals, and in direct contact with the foods and beverages it contains. Tonight, we examine these practical aspects of HDPE, the properties that make it not merely strong, but genuinely fit for the demanding role it plays in our daily lives. Let us begin with temperature, for HDPE containers must function across a remarkable range of thermal conditions. High-density polyethylene remains ductile, meaning it retains the ability to deform without breaking, at temperatures as low as -40 degrees Celsius or -40 degrees Fahrenheit, the point where the Celsius and Fahrenheit scales converge. This low-temperature ductility is extraordinary when we consider that many materials become brittle and prone to shattering as temperatures drop. The molecular basis for HDPE's cold temperature performance lies in the nature of its polymer chains and the way they respond to thermal energy. Even at -40 degrees, the chains retain enough mobility in the amorphous regions to accommodate stress through slight movements and rearrangements. The crystalline regions, while more rigid, are interspersed with these more flexible amorphous zones, creating a material that can still absorb energy and deform rather than crack. This property is essential for containers that might be stored in unheated warehouses during winter months, transported in refrigerated trucks, or kept in home freezers. A milk jug removed from a cold environment and accidentally dropped will not shatter like glass or crack like many other plastics might. The HDPE maintains its integrity, protecting both the container and its contents across the full range of temperatures it is likely to encounter in normal use and distribution. This low-temperature ductility connects directly to HDPE's high-impact resistance, a property we touched upon previously, but which deserves deeper consideration. The ability to prevent cracking when jugs are dropped is not merely a convenience. It is a fundamental requirement for a successful container material. Consider the journey of a milk jug from the dairy to the consumer's refrigerator. It may be dropped during bottling, jostled in transport, knocked from a loading dock, grabbed hastily from a store shelf, and fumbled while being placed in a shopping cart or carried into a home. Each of these events represents a potential impact, a sudden transfer of kinetic energy into the container structure. In a brittle material, any of these impacts could initiate a crack that would compromise the container's ability to hold liquid. HDPE's high-impact resistance means that these everyday mishaps rarely result in failure. When a filled milk jug is dropped, the HDPE wall dents inward at the point of impact, absorbing energy through localized deformation. The polymer chains stretch and slide very slightly in the amorphous regions, dissipating the impact energy as heat and permanent deformation, rather than allowing it to concentrate into a propagating crack. The container may show a white stress mark where chains have been aligned by the impact, but it typically remains intact and functional. This resilience is built into the molecular structure, the long chains, the semi-crystalline morphology, the balance between stiffness and toughness. Beyond resisting single impacts, HDPE must endure repeated mechanical stress without degrading. Each time milk is poured from a jug, the container undergoes a cycle of flexing. The user grips the handle, tilts the jug, and the walls experience changing stress patterns as the weight of the liquid shifts. This action might be repeated dozens of times over the life of the container. Repeated pouring flexes the HDPE chains without causing fatigue cracking, the progressive damage that can occur when a material is cyclically stressed. In metals and some plastics, repeated bending or flexing can cause microscopic cracks to initiate and grow with each cycle until catastrophic failure occurs. HDPE resists this fatigue damage through the resilience of its polymer chains. When the jug is tilted and the wall flexes, chains in the stressed region elongate slightly, with the amorphous regions accommodating most of this deformation. When the stress is released and the jug returns to its normal position, the chains largely return to their original configuration. The crystalline regions act as physical anchors, preventing excessive permanent deformation, while the amorphous regions provide the flexibility needed to accommodate the cyclic stress. This combination allows HDPE to endure hundreds or thousands of flex cycles without accumulating significant damage. The molecular structure essentially resets itself with each cycle, a property that distinguishes tough polymers from materials that accumulate damage over time. Moisture is another factor that can degrade many materials, but HDPE demonstrates exceptional resistance to water absorption. High-density polyethylene absorbs less than 0.01% moisture by weight, an almost negligible amount. This extraordinary hydrophobicity, the tendency to repel water, arises from the chemical nature of the polymer itself. HDPE consists entirely of carbon and hydrogen atoms, forming a nonpolar molecule. Water, in contrast, is highly polar, with partial positive and negative charges distributed across each molecule. The fundamental rule of chemistry that dissolves like applies here. Polar water molecules have no affinity for nonpolar HDPE chains and cannot penetrate the structure to any significant degree. Even when an HDPE container sits in a refrigerator at high humidity or condenses moisture on its exterior surface on a humid day, the material itself does not absorb that moisture into its structure. This is crucial for maintaining the mechanical properties of the container. Materials that absorb moisture often experience swelling, dimensional changes, and reduction in mechanical strength as water molecules interfere with intermolecular bonding. HDPE suffers none of these effects. The container that comes out of refrigerated storage has the same strength, stiffness, and dimensional stability as when it entered, regardless of the moisture conditions it encountered. This resistance to moisture absorption is part of what makes HDPE suitable for long-term storage of beverages, which themselves contain water that could, in a more absorbent material, migrate into the container walls. The chemical inertness of HDPE extends beyond moisture resistance to encompass a broad spectrum of substances. High-density polyethylene does not react with or dissolve in most common chemicals, including the constituents of milk and other foods and beverages. This inertness is essential for preventing flavor or odor transfer to the milk or other contents. Imagine if the container material could leach compounds into the milk, imparting off flavors or odors. The product would be ruined, and the container would fail in its most basic function. HDPE's chemical structure prevents this. The strong carbon-carbon and carbon-hydrogen bonds that form the polymer backbone are stable and unreactive under normal storage conditions. The material does not contain plasticizers, residual monomers, or other additives in significant quantities that might migrate into food products. Regulatory testing has confirmed that HDPE does not impart taste or odor to foods, allowing the milk to retain its natural flavor profile from dairy to consumer. The same inertness that prevents flavor transfer also means that HDPE does not react with the fats, proteins, sugars, and other compounds in milk. Milk is a complex emulsion containing water, fats, proteins, lactose, minerals, and vitamins, yet none of these constituents attack or degrade HDPE. The container remains chemically stable throughout the milk's shelf life, maintaining its integrity and protecting the product within. This chemical inertness and proven safety record have led to HDPE being certified as safe for direct food contact by regulatory agencies around the world. In the United States, the Food and Drug Administration has evaluated HDPE and approved its use in food contact applications. Similar approvals exist in Europe, Asia, and other regions, reflecting a global consensus based on extensive testing. The certification process involves rigorous evaluation of the material's composition, potential for leaching substances into food, toxicity of any compounds that might migrate, and overall safety under conditions of intended use. HDPE has passed these evaluations consistently, demonstrating that it does not pose health risks when used to package foods and beverages. This regulatory approval is not automatic or trivial. It represents years of testing and evaluation by independent scientists and regulatory experts. For consumers, it provides assurance that the milk jug holding their dairy products has been thoroughly vetted for safety. For manufacturers, it provides the legal authorization to use HDPE in food packaging applications. The certification encompasses not just the base polymer, but also approved colorants and any processing aids used in manufacturing, ensuring that the entire material system is safe for its intended purpose. While HDPE excels at chemical resistance and safety, its thermal properties also contribute to its functionality as a container material. The thermal conductivity of HDPE is approximately 0.54 watts per meter Kelvin, a relatively low value that provides modest insulation. Thermal conductivity measures how readily heat flows through a material. Low thermal conductivity means the material is a poor conductor of heat, or conversely, a reasonably good insulator. When a cold gallon of milk in an HDPE jug sits on a kitchen counter, the low thermal conductivity of the jug walls slows the rate at which heat from the room air can warm the milk inside. This is not high-performance insulation by any means. HDPE is no substitute for foam insulation or vacuum walls, but it does provide a degree of thermal protection. The effect is most noticeable over short periods, such as the time it takes to pour a glass of milk and return the jug to the refrigerator. The modest insulation helps maintain the milk's temperature, reducing the rate of warming that would accelerate spoilage. From a molecular perspective, the low thermal conductivity arises because heat transfer through polymers occurs primarily through the vibration and movement of molecular chains, and the semi-crystalline structure of HDPE, with its mixture of ordered crystalline regions and disordered amorphous zones, does not conduct these vibrations particularly efficiently. The result is a material that provides just enough thermal resistance to be beneficial without adding cost or complexity to the container design. Pure high-density polyethylene, in its natural state, is translucent rather than opaque, allowing visibility of the liquid level inside a container. This translucency results from the light-scattering properties we discussed in the first segment, where the crystalline domains scatter light, but do not completely block it. In thin sections, such as the wall of a milk jug, enough light can pass through the scattered and refracted pathways for an observer to perceive the contents. This natural translucency can be an advantage in applications where monitoring the fill level is important. A consumer can see how much milk remains in the jug without opening it. However, for many applications, manufacturers choose to add pigments to HDPE, modifying both its appearance and its properties. The addition of pigments serves multiple purposes beyond aesthetics. Pigments, particularly white titanium dioxide commonly used in milk jugs, actually increase the rigidity of HDPE slightly. The pigment particles, dispersed throughout the polymer matrix, act as additional reinforcement, creating a modest enhancement in stiffness. More importantly, pigments provide light resistance, protecting both the container and its contents from the effects of ultraviolet and visible light. The opaque white coloration so familiar in milk jugs is a deliberate choice that reduces light-induced polymer degradation. While HDPE is relatively stable, prolonged exposure to ultraviolet light can cause photodegradation, where the energy of UV photons breaks chemical bonds in the polymer chains, leading to brittleness and discoloration over time. The white titanium dioxide pigment reflects and scatters light very efficiently, preventing it from penetrating deeply into the polymer where it could cause damage. This protection extends to the milk itself, as certain vitamins in milk, particularly riboflavin and vitamin A, are light-sensitive and can degrade when exposed to light, causing flavor changes. The opaque white jug blocks light transmission, preserving both the container's structural integrity and the milk's nutritional quality and flavor. The choice of white is not merely conventional. It represents an optimization based on light reflection properties, cost-effectiveness of titanium dioxide as a pigment, consumer expectations, and the functional benefits of opacity. Some HDPE containers use other colors for branding or product differentiation, but the principle remains the same. Pigmentation provides protection against light-induced degradation, while allowing the material to maintain its excellent mechanical and chemical properties. As we bring this third segment to a close, we have explored the multifaceted performance characteristics that make HDPE suitable for its demanding role in packaging and product containment. We have seen how the material remains ductile even at -40 degrees Celsius, how its high-impact resistance prevents cracking from drops and impacts, how repeated flexing during normal use does not cause fatigue cracking, how moisture absorption below 0.01% prevents weakening in humid or refrigerated conditions, how chemical inertness prevents any flavor or odor transfer to sensitive products like milk, how regulatory certification confirms its safety for direct food contact, how modest thermal insulation from low thermal conductivity helps protect temperature-sensitive contents, how natural translucency allows liquid-level visibility, how added pigments increase rigidity and light resistance, and how opaque white coloration protects both polymer and product from light-induced degradation. These properties, emerging from and enabled by the molecular structure we explored in earlier segments, work together to create a material that performs reliably across the wide range of conditions encountered from manufacturing through consumer use. In our continuing exploration of high-density polyethylene, we now turn our attention to one of the most critical aspects of this remarkable material: its thermal behavior. Temperature governs not only how HDPE is manufactured and processed, but also how it performs throughout its life cycle, from the heat of the molding process to the temperatures encountered during filling, sterilization, storage, and use. Understanding the thermal properties of HDPE means understanding the transitions that occur within its molecular structure as energy is added or removed, the temperatures at which these transitions take place, and the practical implications for manufacturing and application. Tonight, we immerse ourselves in the thermal world of HDPE, exploring melting points and crystallization temperatures, heat capacities and fusion energies, and the remarkable thermal stability that makes this polymer so versatile. We begin with perhaps the most fundamental thermal property, the melting point. High-density polyethylene has a melting point of approximately 131.8 degrees Celsius, or about 269 degrees Fahrenheit. This is the temperature at which the crystalline regions within HDPE undergo a phase transition from solid to liquid. It is important to understand that polymers do not melt as sharply as pure crystalline substances like ice or metal, because HDPE is semi-crystalline, containing both crystalline and amorphous regions. And because those crystalline regions vary somewhat in their perfection and size, melting occurs over a temperature range rather than at a single precise point. However, the peak melting temperature, the point at which the majority of crystalline material transitions to the molten state, centers around 131.8 degrees Celsius. At the molecular level, this melting process involves the breakdown of the ordered crystalline structure. As thermal energy increases, the polymer chains within the crystalline domains begin to vibrate more vigorously. Eventually, these vibrations overcome the intermolecular forces holding the chains in their parallel, ordered arrangement, and the chains separate, becoming free to move and flow past one another. The material transitions from a solid, where chains are locked in position, to a viscous liquid where chains can slide and entangle freely. This molten state is essential for processing. HDPE must be heated above its melting point to be formed into shapes through blow molding, injection molding, or extrusion. While the melting point defines the temperature at which HDPE becomes fully moldable, finished containers can tolerate brief exposure to temperatures somewhat below, but approaching this melting range. Milk jugs, for instance, can tolerate brief hot fill temperatures around 171 degrees Fahrenheit, which is approximately 77 degrees Celsius. Hot filling is a process where liquid is filled into containers at elevated temperatures to take advantage of the sterilizing effect of heat, and to create a partial vacuum as the contents cool and contract. While 171 degrees Fahrenheit is well below HDPE's melting point, it is warm enough to soften the polymer slightly, particularly in the amorphous regions, which have a lower glass transition temperature. During brief exposure to hot fill temperatures, the container may expand very slightly, and the walls may become temporarily more flexible, but the crystalline structure remains largely intact, providing the structural framework that maintains the container's shape. The key word here is brief. The exposure must be short enough that heat does not penetrate deeply into the polymer or remain long enough to cause significant softening of the crystalline regions. As the hot liquid begins to cool, and as the container itself dissipates heat to the surrounding air, the polymer returns to its normal temperature and properties without having undergone any permanent structural change. However, sustained exposure to higher temperatures will cause permanent deformation of HDPE containers. When the temperature exceeds roughly 220 degrees Fahrenheit, approximately 104 degrees Celsius, and this elevated temperature is maintained for an extended period, the polymer structure begins to suffer lasting changes. At these temperatures, the crystalline regions start to soften significantly, and the material loses its ability to maintain dimensional stability under load. A container exposed to sustained heat in this range will sag, warp, or collapse, especially if it contains liquid or is under any mechanical stress. The deformation is permanent because the polymer chains, once they have moved into new positions while soft and then cooled in those positions, will recrystallize in the deformed configuration. This is why HDPE containers are not suitable for applications involving sustained high heat, such as hot beverages or microwaving. The 220 degree Fahrenheit threshold represents a practical upper limit for sustained use, beyond which the material's structural integrity cannot be maintained. This temperature is still well below the melting point, but it is high enough that the combination of thermal energy and mechanical stress from the container's own weight or its contents will overcome the material's ability to hold its shape. Understanding HDPE's thermal behavior requires examining not just melting, but also the reverse process, crystallization. When molten HDPE cools after molding, crystallization occurs near 121.9 degrees Celsius, or approximately 251 degrees Fahrenheit. This crystallization temperature represents the point at which the polymer chains, which were randomly oriented and freely moving in the molten state, begin to align and pack into ordered crystalline structures. As the temperature drops and thermal energy decreases, the chains lose mobility and the intermolecular forces between them become strong enough to pull them into parallel alignment. This process does not happen instantaneously. It requires time for chains to disentangle from their random configurations and find positions in the crystalline lattice. The crystallization temperature is typically about 10 degrees Celsius below the melting temperature, a phenomenon known as supercooling that reflects the kinetic barrier to forming the ordered structure. During manufacturing, controlling the cooling rate through the crystallization temperature is crucial for determining the final properties of the HDPE product. Slow cooling allows more time for crystallization, potentially increasing the degree of crystallinity and creating larger, more perfect crystalline domains. Rapid cooling produces smaller crystalline regions and may result in lower overall crystallinity, but can be necessary for manufacturing efficiency. The crystallization that occurs during this cooling phase literally locks in the shape of the molded container, as the chains transition from a flowing liquid to a solid, structured material. The energy involved in melting and crystallization is quantified by the latent heat of fusion, which for HDPE is approximately 188.6 kilojoules per kilogram. This value represents the amount of energy required to convert 1 kilogram of crystalline HDPE at its melting point into molten HDPE at the same temperature, or conversely, the amount of energy released when 1 kilogram of molten HDPE crystallizes. The latent heat of fusion reflects the energy needed to overcome the intermolecular forces holding the chains in their crystalline arrangement without changing the temperature of the material. When HDPE is heated to its melting point and begins to melt, the temperature plateaus even as heat continues to be added. All that incoming energy goes into breaking apart the crystalline structure rather than increasing molecular vibration. Similarly, when molten HDPE cools to its crystallization temperature and begins to solidify, it releases this energy back into the surroundings, which is why the temperature plateaus during crystallization as well. The magnitude of HDPE's latent heat of fusion, nearly 190 kilojoules per kilogram, is substantial and reflects the strength of the intermolecular forces in the crystalline regions. For processing, this means that significant energy must be supplied to melt HDPE pellets, and significant energy must be removed to solidify the molten polymer in the mold. The efficiency of heating and cooling systems in molding equipment directly impacts production speed and energy costs. Another important thermal property is specific heat capacity, which for HDPE ranges from approximately 1,331 to 2,400 joules per kilogram Kelvin, depending on chain length and other structural factors. Specific heat capacity measures how much energy is required to raise the temperature of 1 kilogram of material by 1 degree Kelvin, or equivalently, 1 degree Celsius. Materials with high specific heat capacity require substantial energy input to change temperature, while materials with low specific heat capacity heat and cool more readily. HDPE's specific heat capacity, falling in the middle range for polymers, means that moderate energy input is needed to change its temperature. The variation in specific heat with chain length reflects the fact that longer chains have more vibrational modes and conformational degrees of freedom that can absorb thermal energy. A sample of HDPE with higher molecular weight, containing longer chains, will tend toward the upper end of the specific heat range, requiring more energy to heat. The specific heat also varies somewhat with temperature, typically increasing as temperature rises, because higher temperatures activate more molecular motions that can store thermal energy. During processing, the specific heat capacity determines how quickly HDPE pellets will heat up in the barrel of a molding machine, and how quickly the molded part will cool in the mold. It influences cycle times, energy consumption, and the design of heating and cooling systems in processing equipment. One of the remarkable characteristics of HDP is that it cools rapidly without suffering thermal shock. Thermal shock occurs when rapid temperature changes create differential expansion or contraction within a material, generating internal stresses that can cause cracking or fracture. Many ceramics and glasses are highly susceptible to thermal shock. Plunging a hot glass into cold water will likely shatter it. HDP, in contrast, can undergo rapid cooling without this type of damage. The reason lies in the polymer's relatively low thermal conductivity, combined with its ductility and toughness. While rapid cooling does create temperature gradients within the material, the surface cools faster than the interior. The resulting stresses can be accommodated through slight deformation of the polymer chains, rather than through crack formation. The amorphous regions in particular can accommodate some degree of stress through chain movement. Additionally, polymers generally have lower coefficients of thermal expansion than ceramics or glasses, meaning that a given temperature change produces less dimensional change, and therefore less internal stress. For manufacturing, this resistance to thermal shock means that molded HDP parts can be cooled quickly to reduce cycle times without risking damage to the product. A milk jug emerging from the blow mold can be cooled with air or water without concern that rapid cooling will crack the container. The thermal stability of HDP extends to repeated sterilization cycles. The polymer can withstand repeated sterilization at 120 degrees Celsius or approximately 248 degrees Fahrenheit. This temperature is commonly used in autoclaving and other sterilization processes, where steam under pressure achieves temperatures above the normal boiling point of water to ensure that bacterial spores and other resistant microorganisms are killed. 120 degrees Celsius is below HDP's melting point, but above its crystallization temperature, a range where the polymer remains solid but experiences some softening, particularly in regions of lower crystallinity. The key word again is repeated. HDP can endure multiple sterilization cycles without significant degradation. Each cycle subjects the polymer to thermal stress, and over time, repeated heating and cooling can lead to some loss of molecular weight through oxidative degradation, particularly if oxygen is present. However, properly formulated HDP with appropriate antioxidant stabilizers can withstand dozens or even hundreds of sterilization cycles, making it suitable for reusable containers and medical devices that must be sterilized between uses. The crystalline structure provides thermal stability, maintaining the material's integrity even as temperatures approach the crystallization point. This chain thermal stability enables the use of HDP in retort processes, which are used in food preservation. Retorting involves sealing food in a container and then heating it under pressure to temperatures typically ranging from 110 to 130 degrees Celsius. This process sterilizes the food, allowing it to be stored at room temperature for extended periods. For a container material to be suitable for retort processing, it must withstand these elevated temperatures while under the mechanical stress of internal pressure from expanding contents and the external pressure of the retort environment. HDP's chain thermal stability, the resistance of its carbon-carbon backbone to breaking down at elevated temperatures, allows it to maintain structural integrity during retort processing. The chains do not undergo significant degradation or chain scission at these temperatures, provided that exposure times are controlled and appropriate stabilizers are present. While HDP is more commonly used in applications that don't require retort processing, its capability to withstand these conditions expands its potential applications into shelf-stable food products. Finally, we must consider that HDP containers can tolerate internal pressure during sterilized milk production and similar processes. When milk or other liquids are sterilized at elevated temperatures, thermal expansion increases the volume of the liquid, creating pressure inside a sealed or partially sealed container. Additionally, if sterilization generates any vapor or gas, this too contributes to internal pressure. HDPE's combination of tensile strength, flexibility, and thermal stability allows containers to accommodate these internal pressures without rupturing. The container walls may bulge slightly outward, distributing the stress across the polymer structure, but the strong intermolecular forces and the resilience of the long polymer chains prevent catastrophic failure. The material's ability to deform slightly under stress, its ductility, is actually beneficial here, allowing it to accommodate pressure through expansion rather than through brittle fracture. As the sterilized product cools, the internal pressure decreases, and the container may even develop a slight vacuum if sealed, which the HDPE walls can also accommodate by flexing inward. This pressure tolerance is essential for ultra-high temperature processing and other sterilization methods used in modern dairy production. As we conclude this fourth segment, we have journeyed through the thermal landscape of high-density polyethylene, exploring how this material responds to heat and cold across a wide range of temperatures and conditions. We have examined the melting point of approximately 131.8 degrees Celsius, where crystalline regions transition to the molten state, the tolerance of milk jugs to brief hot fill temperatures around 171 degrees Fahrenheit, the permanent deformation that occurs with sustained exposure above 220 degrees Fahrenheit, the crystallization that occurs near 121.9 degrees Celsius as molten polymer solidifies, the substantial latent heat of fusion of 188.6 kilojoules per kilogram that must be added or removed during phase transitions, the specific heat capacity ranging from over 1300 to 2400 joules per kilogram Kelvin that governs how readily the material heats and cools, the rapid cooling without thermal shock that allows efficient manufacturing, the ability to withstand repeated sterilization at 120 degrees Celsius, the chain, thermal stability that enables use in retort processes, and the tolerance for internal pressure during sterilized production. These thermal properties, rooted in the molecular structure and crystalline morphology of HDPE, define both how the material is processed and how it performs in applications involving heat, providing the foundation for its widespread use in food packaging and countless other applications. Having explored the molecular structure, mechanical properties, practical performance characteristics, and thermal behavior of high-density polyethylene in our previous segments, we now arrive at a critical juncture in our journey: the transformation of raw HDPE resin into the finished containers that serve us daily. Manufacturing is where theory becomes reality, where the carefully engineered properties of the polymer are harnessed through precisely controlled processes to create billions of bottles, jugs, and containers each year. Tonight, we delve into the industrial processes that shape HDPE, examining the machinery, temperatures, timing, and techniques that turn small plastic pellets into the familiar milk jug, exploring how each step in the manufacturing process builds upon the material properties we have come to understand. The manufacturing journey begins with HDPE pellets, those small granules of resin that represent the feedstock for container production. These pellets are extruded into molten parasons during jug formation, a process that stands at the heart of blow molding technology. To understand this, we must first grasp what a parison is. A parison is a hollow tube of molten plastic, essentially a thick-walled cylinder of hot, pliable polymer that will become the starting point for the final container shape. The extrusion process that creates the parison begins as HDPE pellets are fed from a hopper into the heated barrel of an extruder. Inside this barrel, a rotating screw conveys the pellets forward while simultaneously mixing them and subjecting them to increasing temperature. As the pellets move through the heated zones of the barrel, they soften, melt, and transform into a viscous, homogeneous melt. The screw's rotation not only pushes this molten material forward, but also generates additional heat through shear forces as polymer chains slide past one another. The molten HDP, now a thick, honey-like liquid at temperatures above 130 degrees Celsius, accumulates at the end of the barrel. At the precise moment in the manufacturing cycle, this molten polymer is forced through an annular die, a ring-shaped opening that forms the molten material into a hollow tube. This tube, the PolymerScience, hangs downward from the die, suspended by its own viscosity and surface tension, awaiting the next stage of transformation. The PolymerScience walls typically measure 1 to 2 millimeters in thickness, a dimension carefully controlled to ensure that sufficient material is present to form the final container walls, while avoiding excess material that would be wasteful and would slow cooling. This thickness represents a delicate balance. Too thin, and the PolymerScience may rupture during the subsequent blow molding step, or may not contain enough polymer to reach all areas of the mold cavity, particularly complex features like handles. Too thick, and the PolymerScience wastes material, takes longer to cool, and increases cycle time and cost. The 1 to 2 millimeter range has been optimized through decades of manufacturing experience and engineering analysis. At this thickness, the molten polymer possesses enough structural integrity to hang vertically without collapsing under its own weight, while remaining thin enough to be blown efficiently into the final shape. The uniformity of this wall thickness along the length of the PolymerScience is crucial. Variations can lead to thin spots in the final container or to uneven material distribution. Modern extrusion systems incorporate precise controls that adjust die geometry dynamically, compensating for factors like gravity-induced sagging and ensuring that the PolymerScience maintains consistent wall thickness from top to bottom. The transformation from PolymerScience to finished container occurs through blow molding, a process that expands polymer chains uniformly against cooled molds. As soon as the PolymerScience reaches the desired length, the two halves of the blow mold close around it, capturing the molten tube between precisely machined metal surfaces. These mold halves contain the negative image of the desired container shape. All the contours, the handle, the threads for the cap, the flat surfaces and corners. At the moment the mold closes, the bottom of the PolymerScience is pinched shut, sealing one end of the tube. Immediately, a blow pin inserts into the open top of the PolymerScience and pressurized air rushes in. This air, typically at pressures of several atmospheres, forces the molten polymer outward in all directions, pressing it against the cooled mold surfaces. The expansion happens rapidly, but not instantaneously. The viscous HDP flows and stretches, with the polymer chains elongating and orienting as they are drawn through space. This orientation, where chains align somewhat in the direction of stretching, actually enhances certain properties of the final container, providing additional strength in directions that will experience stress during use. The cooled mold surfaces, maintained at temperatures between 10 and 30 degrees Celsius, immediately begin extracting heat from the polymer as soon as contact is made. This rapid cooling initiates crystallization, freezing the chains in the configuration imposed by the mold shape. Within seconds, the polymer has solidified enough to retain its form, and the mold can open to release the finished container. The efficiency of modern manufacturing is remarkable, with reciprocating screw machines enabling cycle times under 10 seconds. A reciprocating screw machine combines the plasticizing function of a screw extruder with the shot delivery function of a plunger. The screw rotates to melt and mix the polymer, but it also reciprocates, moves forward and backward along its axis. As the screw rotates and pellets melt, the accumulating molten polymer pushes the screw backward, creating a reservoir of melt in front of the screw. When it is time to form the next PolymerScience, the screw stops rotating and instead acts as a plunger, driving forward to push the accumulated melt through the die. This reciprocating action allows precise control over shot size and timing, and it enables very rapid cycles. In less than 10 seconds, a modern machine can extrude a PolymerScience, close the mold, blow the container, cool it sufficiently, open the mold, eject the part, and prepare the next shot of molten material. This extraordinary speed is achieved through careful optimization of every aspect of the process. Rapid mold closing and opening mechanisms, efficient cooling channels within the mold, powerful hydraulic or electric actuators, and precisely controlled temperatures and pressures throughout the system. The sub-10-second cycle time means that a single machine can produce hundreds of containers per hour, making mass production economically viable. One of the challenges in blow molding complex shapes like milk jugs is ensuring structural integrity at seams and joints. Two-stage mold closing strengthens welding lines in handles and bases, addressing this challenge through a clever modification of the basic blow molding process. Welding lines, also called knit lines, occur wherever two flows of molten polymer meet and must fuse together. In a milk jug, critical welding lines occur at the base where opposite sides of the PolymerScience are pinched together, and in the handle where material flows around the void that will become the handle opening. These welding lines can be weak points if the polymer chains on each side do not interdiffuse and entangle sufficiently. Two-stage mold closing addresses this by first partially closing the mold to a position that allows controlled contact and fusion at critical points, giving chains time to entangle before full pressure is applied. Then the mold completes its closing action, and blow pressure expands the PolymerScience fully. This staged approach ensures that welding lines receive additional time and pressure to form strong molecular bonds, reducing the risk of failure at these critical locations. The result is a container where handles can support the full weight of the contents without risk of separation, and where base seams resist the stress of being set down repeatedly. Throughout the molding process, careful control of temperature is essential. Low melt temperatures preserve polymer chain integrity by minimizing the thermal and oxidative degradation that can occur when polymers are held at elevated temperatures. While HDPE must be heated above its melting point of approximately 132 degrees Celsius to become processable, there is no benefit to heating it far above this temperature, and doing so risks harm. At excessive temperatures, particularly in the presence of oxygen, polymer chains can undergo scission, breaking into shorter segments. This degradation reduces molecular weight, which in turn reduces mechanical properties like tensile strength and impact resistance. By maintaining melt temperatures at the minimum necessary for good flow and processing, typically in the range of 170 to 230 degrees Celsius, manufacturers preserve the integrity of the long polymer chains that give HDPE its excellent properties. Modern processing equipment incorporates multiple temperature zones, each precisely controlled, and residence times are minimized to reduce the duration that polymer spends at elevated temperature. Antioxidant stabilizers added to the resin provide additional protection against thermal degradation during processing. On the opposite end of the thermal spectrum, mold temperatures between 10 and 30 degrees Celsius accelerate crystallization and solidification of the blown container. The mold, typically constructed of aluminum or steel for good thermal conductivity, contains internal cooling channels through which chilled water circulates continuously. This cooling system maintains the mold surfaces at temperatures well below the crystallization temperature of HDPE, creating a steep temperature gradient when molten polymer contacts the mold. This gradient drives rapid heat extraction, pulling thermal energy from the polymer and promoting fast crystallization. The choice of mold temperature within the 10 to 30 degrees Celsius range depends on several factors. Cooler temperatures, near 10 degrees, provide faster solidification and shorter cycle times, but may result in higher internal stresses in the part and could potentially cause surface defects from too rapid cooling. Warmer temperatures, near 30 degrees, allow more gradual cooling and may produce parts with lower stress and better surface finish, but extend cycle time. The optimal temperature is determined empirically for each product design, balancing cycle time against part quality. HDPE milk jugs are produced using single-layer construction, meaning the container wall consists of just one layer of polymer rather than multiple layers of different materials. This monolithic structure offers several advantages. Single-layer construction is simpler and less expensive than multi-layer alternatives, requiring less complex equipment and fewer process controls. It also makes recycling straightforward. The entire container is HDPE, so it can be ground up and reprocessed without the need to separate different materials. The single layer is possible because HDPE itself provides all the necessary properties: strength, chemical resistance, moisture barrier, and food safety. In contrast, some packaging applications require multiple layers to achieve combinations of properties that no single material provides. For example, combining oxygen barrier layers with moisture barrier layers and structural layers. HDPE milk jugs need no such complexity. The molecular structure and processing of HDPE give it sufficient barrier properties to protect milk during its typical shelf life, adequate strength to contain the liquid, and suitable food contact safety. The simplicity of single-layer construction contributes to the economic efficiency that has made HDPE the dominant choice for milk packaging. We noted earlier that colorants and pigments are added to HDPE, and their role extends beyond aesthetics. Colorants act as radiation and oxygen barriers within the polymer matrix, providing functional benefits that enhance container performance and longevity. White titanium dioxide, the most common pigment in milk jugs, consists of tiny particles with exceptional light-scattering properties. These particles, dispersed throughout the HDPE matrix, intercept photons of light before they can penetrate deeply into the material or reach the contents. By scattering and reflecting light, the pigment prevents ultraviolet radiation from causing photodegradation of the polymer chains. Simultaneously, the pigment particles may provide some obstruction to oxygen diffusion through the polymer, creating a tortuous path that slightly enhances the already good barrier properties of HDPE. While HDPE itself is a reasonably good oxygen barrier due to its crystallinity and tight chain packing, the addition of pigment particles can provide incremental improvement. This dual function, protecting both the polymer and the product, makes pigmentation a valuable feature rather than merely a cosmetic choice. Finally, we must recognize the immense scale of HDPE container production. Milk bottles account for roughly 1/3 of global HDPE applications, representing billions of containers manufactured annually worldwide. This staggering volume reflects both the ubiquity of dairy consumption and the dominance of HDPE as the material of choice for this application. 1/3 of all the high-density polyethylene produced globally goes into milk bottles and similar dairy containers, gallons, half-gallons, quarts, and various other sizes, in countries around the world. This represents hundreds of thousands of tons of polymer each year, transformed through the processes we have discussed into containers that will hold and protect one of humanity's most fundamental food products. The scale of production has driven continuous improvement in manufacturing efficiency, quality control, and material utilization. It has also created a substantial recycling stream, as used milk jugs represent one of the most commonly recycled plastic items. Their HDPE material valuable for reprocessing into new products. As we conclude this fifth segment of our exploration, we have witnessed the transformation of HDPE from pellet to finished product through the sophisticated processes of modern manufacturing. We have seen how pellets are extruded into molten parissons, how parison walls of 1 to 2 millimeters provide the material for container formation, how blow molding expands polymer chains uniformly against cooled molds to create the final shape, how reciprocating screw machines achieve remarkable cycle times under 10 seconds, how two-stage mold closing strengthens critical welding lines in handles and bases, how low melt temperatures preserve the integrity of polymer chains during processing, how mold temperatures between 10 and 30 degrees Celsius accelerate crystallization and solidification, how single-layer construction provides simplicity and recyclability, how colorants serve as radiation and oxygen barriers within the polymer, and how milk bottles represent roughly 1/3 of global HDPE applications. These manufacturing processes, refined over decades of industrial practice, harness the inherent properties of HDPE to create containers of remarkable utility and efficiency, transforming molecular science into everyday objects. As we continue our journey through the world of high-density polyethylene container manufacturing, we now focus our attention on the critical details that separate adequate production from true manufacturing excellence. The transformation of HDPE pellets into finished containers, which we explored in our previous segment, requires not only the right equipment and processes, but also extraordinary precision in dimensions, meticulous quality control, and careful attention to compatibility between different materials and components. Tonight, we examine the exacting standards and sophisticated techniques that ensure each milk jug meets the stringent requirements for food safety, structural integrity, and consumer satisfaction. These are the details that make the difference between a container that performs flawlessly and one that fails in service. We begin with a seemingly simple but critically important specification. HDPE milk jugs use standardized 38 to 400 neck finishes. This numerical designation, cryptic to the uninitiated, actually encodes precise dimensional information that ensures universal compatibility between containers and closures. The number 38 refers to the outer diameter of the container's threaded neck finish, measured in millimeters. The number 400 indicates the thread style and configuration according to industry standards established by organizations like the Society of the Plastics Industry. This standardization means that any 38 to 400 closure, whether manufactured by the container producer, the dairy, or a third-party cap supplier, will fit properly on any 38 to 400 container neck. The threads are precisely specified in their pitch, depth, and profile, ensuring consistent engagement between cap and container. This dimensional precision must be maintained within tolerances of fractions of a millimeter, as variations could result in caps that are too loose, allowing leakage, or too tight, making opening difficult or damaging the threads. The blow mold cavity that forms the neck is machined to exacting specifications, and the cooling of this region is carefully controlled to prevent shrinkage that would alter dimensions. The standardization extends beyond just dimensions to include features like tamper evidence bands, venting systems, and the sealing surface where the closure liner contacts the container. This universal standard, developed through industry collaboration over decades, enables the efficient, interchangeable systems that modern distribution requires. The closure itself typically incorporates a liner that creates the actual seal against the container opening. LDP liners seal against HDPE necks without chemical migration, a pairing that reflects careful material selection based on compatibility. LDP, or low-density polyethylene, is a cousin to HDPE within the polyethylene family, sharing the same basic chemical composition, carbon and hydrogen, but differing in structure. LDP has significant branching along its polymer chains, giving it lower density, greater flexibility, and softer texture compared to HDPE. These properties make LDP ideal for sealing liners, as the material can deform slightly to conform to the sealing surface, creating a reliable seal even if microscopic imperfections exist on the HDPE neck finish. The liner compresses between the cap and the container rim, and the soft LDP flows into any tiny irregularities, blocking potential leak paths. Critically, because both materials are polyethylene, there is no chemical incompatibility between them. They will not react with each other, and components will not migrate from one to the other in ways that could contaminate the milk or compromise the seal. Both materials are approved for food contact, and their chemical similarity means that recyclers can process them together without the complications that arise when dissimilar polymers are mixed. The LDPE liner bonds to the closure, typically through heat or adhesive, and when the consumer first opens the container, the liner may remain behind on the neck finish or may pull away with a tamper-evident ring, providing visual evidence that the container has been opened. In the interest of sustainability and cost efficiency, manufacturers often incorporate recycled HDPE into new containers. However, regrind content is limited to maintain food safety and strength. Regrind refers to recycled HDPE that has been ground into small particles and can be mixed with virgin resin. This material might come from post-industrial sources, such as rejected containers or trimmed material from the manufacturing process itself, or from post-consumer sources, such as collected and processed milk jugs that consumers have used and discarded. While using regrind reduces waste and conserves resources, regulations and quality standards limit how much can be used in food contact applications. Post-consumer regrind, in particular, must be carefully controlled because the history of the material cannot be fully known. It may have been exposed to contaminants, degraded through outdoor weathering, or stressed through previous use. Regulatory agencies like the FDA provide guidelines on acceptable levels and processing methods for recycled content in food packaging. Typically, regrind content in milk jugs is limited to a certain percentage, often in the range of 25 to 50%, with the remainder being virgin resin. Some designs use a multi-layer approach where recycled content is sandwiched between virgin layers, ensuring that only virgin material contacts the food. The limitation on regrind content also serves to maintain mechanical properties. Recycled polymer may have reduced molecular weight from degradation during its previous life cycle, potentially reducing strength and impact resistance. By blending it with virgin material, manufacturers maintain properties within specifications while still benefiting from the sustainability and cost advantages of recycling. Quality control in container manufacturing involves multiple inspection and testing methods, with vacuum decay testing being one of the most sensitive techniques for detecting microleaks in finished containers. This non-destructive test can identify leaks far smaller than those detectable by visual inspection, or even by pressurizing the container with air and submerging it in water to look for bubbles. In vacuum decay testing, the container is placed in a sealed test chamber, and the chamber is evacuated to create a vacuum. If the container has any leak, however minute, air from inside the container will flow out into the vacuum chamber, causing a measurable change in pressure. By monitoring the pressure in the chamber over time, the test system can detect leaks through defects as small as a few micrometers. These microleaks might result from contamination in the resin that creates voids in the container wall, from incomplete fusion at weld lines, from pinholes caused by trapped gases during molding, or from cracks initiated during ejection from the mold. A container that passes vacuum decay testing is virtually guaranteed to be leak-free under normal use conditions. The sensitivity of this method makes it ideal for quality assurance, and modern manufacturing lines can incorporate automated vacuum decay testers that check every container or statistically significant samples at high speed, rejecting any that fail to meet the stringent leak specifications. Many quality issues in blow-molded containers trace back to thermal management during the molding process. Symmetrical mold cooling prevents tilted necks, a common defect that can render containers unusable. If one side of the mold cools faster than the other, the polymer on that side will crystallize and shrink sooner, creating differential stresses that can pull the neck out of vertical alignment. A tilted neck creates problems. The container may not stand upright properly. Caps may not seal correctly due to uneven contact with the sealing surface, and the appearance is unacceptable to consumers and brands. Achieving symmetrical cooling requires careful design of the cooling channels within the mold, ensuring that chilled water flows uniformly around all areas of the cavity. The channels must be positioned at consistent distances from mold surfaces, with flow rates and temperatures balanced to provide equal cooling on all sides. Temperature sensors at multiple points on the mold can verify that symmetrical conditions are maintained, and adjustable flow valves allow fine-tuning of the cooling in different zones. The attention to thermal uniformity extends beyond just the neck to the entire container. Uneven cooling anywhere can create warpage, dimensional variations, or internal stresses that may cause delayed failure. Symmetrical cooling is both a science and an art, requiring understanding of heat transfer, fluid dynamics, and the crystallization behavior of HDPE. At the moment when the blow pin descends to introduce pressurized air into the PolymerScience, precise alignment is essential. Blow pin nozzle gaps must match PolymerScience thickness precisely to ensure proper air introduction without damaging the molten polymer. The blow pin is a hollow needle or tube that penetrates into the PolymerScience from above after the mold closes. If the gap between the blow pin nozzle and the PolymerScience wall is too large, air may escape around the pin rather than inflating the PolymerScience efficiently, or turbulence in the air flow may create defects. If the gap is too small, the pin may puncture the PolymerScience wall or create excessive friction that tears the molten material. The ideal gap is typically just slightly larger than necessary to allow air passage, perhaps a fraction of a millimeter, and achieving this requires that the PolymerScience wall thickness be consistent and that the blow pin be positioned accurately in the center of the PolymerScience. Since PolymerScience thickness can vary slightly from shot to shot due to changes in melt temperature, extrusion speed, or material properties, sophisticated control systems monitor these variables and make real-time adjustments to maintain the optimal relationship between pin position and PolymerScience dimensions. Some systems even incorporate sensors that measure PolymerScience wall thickness optically and adjust blow pin position or timing accordingly. During the expansion of the PolymerScience against the mold walls, air must be able to escape from the mold cavity or it will become trapped, preventing complete formation of the container. Vent holes allow trapped air to escape during expansion, ensuring that the molten HDPE can reach every corner and detail of the mold. These vents are typically tiny channels, often just a few hundredths of a millimeter wide, cut into the mold parting line or positioned at strategic locations where air tends to become trapped, such as in corners or in the handle region. The vents must be large enough to allow air to escape rapidly, but small enough that molten HDPE cannot be forced through them under blow pressure. Finding this balance requires understanding the viscosity of molten HDPE at processing temperatures and the pressures involved in blow molding. If vents are too large, polymer will extrude through them, creating flash, thin webs of material along the parting line that must be trimmed away. If vents are too small or become clogged, trapped air prevents complete filling, resulting in voids, weak spots, or incomplete features. Regular maintenance of vents, cleaning them of any accumulated polymer or debris, is essential for consistent part quality. The strategic placement of vents reflects detailed knowledge of how air moves within the mold cavity as the PolymerScience expands, with computational fluid dynamics sometimes used to optimize vent location. The extrusion of the PolymerScience itself requires precise timing to ensure that the correct amount of molten polymer is delivered at exactly the right moment in the molding cycle. Servo motors control PolymerScience extrusion timing with a level of precision impossible with older hydraulic or mechanical systems. A servo motor is an electric motor with sophisticated feedback control that can position its shaft to fractions of a degree and accelerate or decelerate with precise profiles. In the reciprocating screw machine, servo motors may control both the rotation of the screw during plasticizing and its forward stroke during injection. By programming the exact speed profile, the system can extrude the Polyethylene with controlled velocity, starting slowly to allow clean separation from the previous shot, accelerating to deliver material efficiently, and decelerating smoothly to create a clean cutoff. This precision ensures that the Polyethylene length is consistent from shot to shot, that the wall thickness profile is repeatable, and that the Polyethylene is ready at exactly the moment when the mold closes. Variations in Polyethylene delivery timing would cause the Polyethylene to be in the wrong position when the mold captures it, leading to uneven material distribution or even pinched sections where mold has cut through the Polyethylene prematurely. Servo control has revolutionized blow molding, enabling the extremely short cycle times and high consistency that modern production demands. The formation of the container's base is particularly critical, as this surface must be flat and strong enough to support the container when filled. Pneumatic pressure consistency ensures full bottom formation without weak areas or incomplete filling. The air pressure introduced through the blow pin must be maintained at a consistent level throughout the blow phase to ensure that molten HDPE is forced into all areas of the base evenly. Variations in pressure could result in thicker areas where higher pressure pushed more material and thinner areas where lower pressure allowed incomplete expansion. The base typically includes structural features like ribs or a slightly domed profile to enhance stability and strength. And these features require that polymer be forced into relatively deep, narrow sections of the mold. Consistent pneumatic pressure ensures complete filling of these features. Modern blow molding machines incorporate precision pressure regulators and real-time monitoring of the air supply to maintain consistency. The pressure profile may even be programmed to vary during the blow cycle, starting with lower pressure to initiate expansion gently, then increasing to ensure complete filling, and finally releasing as the polymer solidifies. This controlled pressure application is made possible by electronic pneumatic valves and feedback control systems that respond within milliseconds to maintain the desired pressure curve. With all these precision controls and quality systems in place, manufacturers establish rigorous quality targets. Quality targets aim for defect rates below 2%, meaning that fewer than 2 containers out of every 100 produced should have any defect that would cause rejection. In practice, many modern facilities achieve defect rates well below 1%, approaching zero defect performance through statistical process control and continuous improvement. A defect might be a visual flaw like surface roughness or discoloration, a dimensional issue like an out-of-tolerance neck finish, a structural problem like incomplete handle formation, or a leak detected during testing. Achieving these low defect rates requires not just good equipment, but also rigorous monitoring, frequent sampling and inspection, operator training, preventive maintenance, and a culture of quality throughout the organization. Statistical process control charts track key parameters over time, allowing operators to detect trends before they result in defects, and to make adjustments that keep the process centered on optimal settings. When defects do occur, root cause analysis determines whether the issue stems from material variation, equipment wear, process drift, or human error, and corrective actions prevent recurrence. The economic imperative is clear. Every defective container represents wasted material, energy, and time, and in a high-volume operation producing thousands of containers per hour, even a 1% defect rate translates to significant waste. Conversely, achieving sub-2% defect rates ensures efficient use of resources and reliable supply of quality containers to customers. As we conclude this 6th segment, we have explored the precision engineering and meticulous quality control that characterize modern HDPE container manufacturing. We have examined how standardized 38 to 400 neck finishes ensure universal compatibility with closures, how LDP liners seal against HDPE necks without chemical migration, how regrind content is carefully limited to maintain food safety and mechanical properties, how vacuum decay testing detects microleaks with extraordinary sensitivity, how symmetrical mold cooling prevents defects like tilted necks, how blow-pin nozzle gaps must match PolymerScience thickness precisely for successful air introduction, how vent holes allow trapped air to escape during expansion, how servo motors control PolymerScience extrusion timing with unprecedented precision, how pneumatic pressure consistency ensures complete formation of critical features like the base, and how ambitious quality targets drive defect rates below 2%. These elements of precision and quality assurance, built upon the foundation of material science and process engineering we have explored in earlier segments, ensure that HDPE containers perform their function reliably, safely, and efficiently, meeting the demanding standards of modern food packaging. In our exploration of high-density polyethylene container manufacturing, we have focused primarily on successful production, the processes, properties, and precision controls that yield quality containers. Yet no examination of manufacturing would be complete without understanding what can go wrong and why. Defects in blow-molded containers are not random occurrences, but rather the visible manifestations of specific process deviations or material conditions. Each type of defect tells a story, providing clues about temperature imbalances, timing errors, material inconsistencies, or equipment malfunctions. Tonight, we turn our attention to the various defects that can affect HDPE containers, exploring their root causes and the intricate relationships between processing conditions and final product quality. Understanding these defects is essential not only for preventing them, but also for appreciating the sophistication required to manufacture billions of containers with consistently high quality. We begin with gate leaks, defects that form when PolymerScience walls are too thin at mold entry points. To understand this defect, we must first recognize that the PolymerScience does not have perfectly uniform wall thickness along its entire length. Gravity causes the hanging PolymerScience to sag slightly, creating natural variations where material accumulates more in some regions and stretches thinner in others. Additionally, the extrusion die itself may not produce perfectly uniform thickness if where contamination or thermal variations affect flow. When the mold closes around the PolymerScience and the blow air inflates it, the thinnest regions must stretch the farthest to reach the mold walls. If a thin spot exists at a critical location, particularly near where the blow pin enters or where the mold first makes contact, the material may stretch beyond its capacity, creating a weak point or even a pinhole through which air can leak during blowing. These gate leaks prevent proper inflation of the container, resulting in parts that are incompletely formed or collapsed. The molecular explanation relates to the limited extensibility of semi-crystalline polymers. While the molten HDPE can flow and stretch, there are limits to how much the chains can elongate before they lose cohesion. When wall thickness is insufficient at a critical point, the stretching required exceeds what the material can sustain, and rupture occurs. Preventing gate leaks requires careful control of PolymerScience programming to ensure adequate wall thickness at all critical locations, proper die maintenance to ensure uniform extrusion, and appropriate melt temperature to give the polymer adequate extensibility. Another common defect involves the dimensional accuracy of the container opening. Oval necks result from insufficient mold cooling, creating a situation where the polymer has not solidified adequately when the mold opens and the part is ejected. The neck finish must be perfectly circular to seal properly with closures, but if the polymer is still soft when released from the mold, the weight of the container and any handling forces can distort the opening from round to oval. This distortion occurs because the chains in the neck region have not yet crystallized sufficiently to lock the structure rigidly into place. The neck, being a relatively thick section compared to the container walls, retains heat longer and cools more slowly. If the mold opens too soon, or if cooling in the neck area is inadequate, the surface may appear solid while the interior remains soft. As the part is ejected and handled, this soft core allows deformation. The molecular motion that should have been frozen by crystallization continues, allowing chains to slide past one another under stress. Oval necks create immediate problems. Caps will not thread on properly, sealing becomes unreliable, and the containers must be rejected. The solution involves ensuring adequate cooling time before mold opening, improving cooling in the neck region through optimized mold design, and possibly reducing melt temperature to accelerate solidification. Some molds incorporate specifically designed cooling inserts in the neck area to address this common issue. The base of the container presents its own challenges, with rocker bottoms being a particularly troublesome defect. Rocker bottoms occur when blow air fails to fully exhaust from the container after molding, leaving residual pressure inside as the part cools. This trapped air creates internal pressure that can deform the base, causing it to bulge slightly downward in the center. When such a container is placed on a flat surface, it rocks because the center sits lower than the outer rim, or conversely, the center may bulge upward, creating a dome that makes the container unstable. The defect arises during the exhaust phase of the blow molding cycle. After the container has been inflated and the polymer has contacted the mold walls, the blow air must be vented out before the mold opens. If the exhaust valve does not open fully, or if it does not remain open long enough, or if there is a restriction in the exhaust line, some air remains trapped. As the polymer cools and solidifies, it becomes more rigid, but the trapped air continues to exert pressure against the walls. The base, being a relatively flat and flexible section, is particularly susceptible to this pressure, deforming outward. At the molecular level, the polymer chains are attempting to crystallize in a stress-free configuration, but the internal air pressure creates stress that becomes locked into the structure as it solidifies. Preventing rocker bottoms requires reliable exhaust systems, adequate exhaust time in the cycle, and inspection of exhaust valves and passages to ensure they function correctly. At the points where the mold pinches the PolymerScience shut, typically at the bottom of the container and sometimes at the handle, proper sealing is critical. Tearing at pinch-off lines happens when chains remain too molten at the moment the mold closes. The pinch-off should create a clean weld where the two opposing faces of the PolymerScience are pressed together and fuse into a single, strong seam. This fusion requires that the polymer chains on each face interdiffuse, entangling across the interface to create molecular continuity. However, if the polymer is too hot and fluid when pinched, the material may flow excessively rather than forming a stable weld. The high fluidity allows the polymer to squirt out from between the mold halves, creating thin, weak sections. Worse, the flowing material may tear, creating holes or separation at the pinch line. Additionally, if the polymer is too molten, it has low viscosity and low strength, making it unable to support the stresses imposed during the subsequent blow phase. When air pressure inflates the PolymerScience, these weak pinch-off regions may rupture. The molecular basis relates to temperature-dependent viscosity. Hotter polymer flows more easily, but has less strength. The optimal condition is polymer that is soft enough to weld intimately, but viscous enough to resist flowing excessively under the pinching force. Controlling pinch-off tearing requires optimization of melt temperature, potentially localized cooling of the PolymerScience in regions where pinching occurs, proper pinch-off force and geometry in the mold design, and timing that allows slight cooling before the mold fully closes. During the inflation process, achieving uniform expansion of the PolymerScience is essential for consistent wall thickness in the final container. Horizontal ring lines form from uneven Polyethylene inflation, creating visible bands that circle the container horizontally. These lines result from regions where inflation was not smooth and continuous, but instead occurred in steps or surges. The cause often relates to variations in the polyethylene wall thickness or temperature. If the polyethylene has a band of thicker or cooler material at some height, that region will resist expansion more than the surrounding areas. As blow pressure increases, the thinner or hotter regions expand first. Then the resistant band suddenly yields and expands rapidly, creating a line marking the transition. These ring lines are not merely cosmetic. They often coincide with regions of stress concentration or unusual molecular orientation that can affect mechanical properties. The chains in a ring line region may be highly oriented due to the rapid stretching, or they may show evidence of the strain history in their crystalline morphology. From a troubleshooting perspective, horizontal ring lines point to polyethylene quality issues. Solutions include improving die uniformity, optimizing polyethylene programming to create more consistent wall thickness, ensuring uniform melt temperature, and potentially adjusting blow pressure profiles to encourage more gradual, even expansion. While horizontal lines suggest circumferential variations, vertical defects indicate different root causes. Vertical streaks indicate foreign material in the extrusion die, contamination that interferes with smooth flow of the molten polymer. The die, through which molten HDPE flows to form the polyethylene, must present a clean, smooth surface for the polymer to flow uniformly. If a particle of degraded polymer, a bit of metal from wear, a fiber of cloth from cleaning materials, or any other foreign material becomes lodged in the die, it creates a disruption in the flow field. Polymer flowing around this obstruction creates a wake region with altered flow characteristics, and this disturbance propagates downstream into the polyethylene as a vertical line or streak. Because the die is stationary and the polyethylene is continuously extruded, the defect appears as a continuous vertical feature. These streaks are usually visible as lines of different texture, color, or transparency running the length of the container. At the molecular level, the streak region may have different molecular orientation, different thermal history, or even different composition if the contamination is introducing foreign material into the melt stream. Vertical streaks compromise both appearance and potentially structural integrity. Elimination requires stopping production, disassembling and thoroughly cleaning the die, inspecting for wear or damage that might generate metal particles, and ensuring that resin handling systems prevent contamination. Filtration screens in the extrusion system can catch larger particles, though very fine contamination may pass through. Internal defects can be as problematic as surface features. Wall bubbles arise from trapped gases or moisture within the polymer structure. These bubbles appear as voids within the container wall, visible as lighter spots or actual hollow regions that weaken the structure. The source of the gas can be moisture that was absorbed by the HDPE pellets before processing, volatile compounds from additives or contaminants, or gases generated by thermal degradation if the polymer is overheated. When moisture-laden pellets are melted, the water vaporizes, creating bubbles in the melt. Similarly, if polymer degradation occurs, the breakdown reactions can generate gases like carbon dioxide or volatile organic compounds. During extrusion and blowing, these gases may become trapped in the polymer, and as the material cools and solidifies, the bubbles are frozen into place. The presence of these voids reduces the effective wall thickness in those locations, creating weak points that may fail under stress. At the molecular level, the voids represent discontinuities in the polymer structure, regions where no material is present to carry loads. Preventing wall bubbles requires proper drying of HDPE resin before processing, typically by holding it in a hot air dryer that drives off absorbed moisture. It also requires controlling melt temperature to prevent degradation, and ensuring that the vacuum venting on the extruder effectively removes any volatiles from the melt before it reaches the die. Surface texture affects both the appearance and performance of containers. Orange peel surfaces result from uneven crystallization rates across the surface of the molded part. An orange peel texture looks much like the dimpled surface of an orange skin, with small-scale roughness that gives the container a matte rather than glossy appearance. This texture arises when crystallization does not proceed uniformly. If some regions of the surface cool slightly faster or slower than others, or if local variations in stress or molecular orientation affect crystallization kinetics, then the crystalline structures that form will vary in size and distribution. These variations create surface irregularities at the scale of micrometers to tens of micrometers. The defect is particularly common if mold temperature is not well controlled, or if there are hot or cold spots on the mold surface. Local variations in cooling rate translate directly into variations in crystallization behavior. Smoother surfaces result from uniform, controlled cooling that promotes consistent crystallization. While orange peel texture may be acceptable or even desirable in some applications for aesthetic reasons or to reduce gloss, in most cases a smooth surface is preferred. Achieving it requires excellent mold temperature control, properly designed cooling channels, and possibly mold surface treatments that enhance heat transfer uniformity. The bottom of the container, being a critical structural and functional feature, is susceptible to several specific defects. Bottom wrinkles form due to overheating or mistimed pre-blowing, creating folds or creases in the base that weaken it and create an unacceptable appearance. Pre-blowing is a technique where a small amount of air is introduced before the mold fully closes, partially inflating the parison and positioning it in the mold cavity. If pre-blowing occurs too early, before the mold has captured and constrained the parison properly, the parison may inflate unevenly or shift position, creating folds when the mold finally closes and full blow pressure is applied. These folds become locked into the structure as wrinkles. Overheating contributes to this defect by making the polymer too soft and fluid, allowing it to flow excessively and fold under the complex stresses of inflation. The base region undergoes significant deformation during blow molding. The flat bottom of the parison must expand outward and down to fill the base cavity. And if the material is too hot, this deformation can occur in an uncontrolled manner that creates wrinkles. The molecular chains in wrinkled regions show evidence of the complex strain history, with unusual orientation patterns and potential stress concentration. Preventing bottom wrinkles requires precise control of pre-blow timing and pressure, appropriate melt temperature, and proper parison positioning in the mold. Finally, defects can occur even in the finishing operations after the container is molded. Finish trim defects create jagged sealing surfaces on the neck, where the closure liner must seal. After blow molding, there is often excess material, or flash, at the parting line of the mold or at the top of the neck where the parison was pinched and cut. This flash must be trimmed away to create the clean sealing surface required for proper closure function. Trimming may be done while the part is still in the mold, immediately after ejection using spinning knives or blades, or in a secondary operation. If trimming tools are dull, misaligned, or improperly set, they can create rough, jagged edges instead of clean cuts. A jagged sealing surface will not seal properly with the closure liner. There will be gaps where liquid can escape or air can enter. Additionally, sharp projections from jagged trimming can damage the liner itself during capping. The quality of the trim depends on sharp, well-maintained cutting tools, proper alignment and clearances in the trimming mechanism, and appropriate timing, so that trimming occurs when the polymer has the right consistency, solid enough to cut cleanly, but not so hard that it shatters or cracks. Regular inspection and replacement of trimming blades is essential preventive maintenance. As we conclude this 7th segment, we have examined the various defects that can occur in HDPE container manufacturing and the specific process conditions that cause them. We have explored how gate leaks form when Polyethylene walls are too thin at critical points, how oval necks result from insufficient cooling before ejection, how rocker bottoms occur when blow air is not fully exhausted, how tearing at pinch-off lines happens when polymer remains too molten during mold closing, how horizontal ring lines form from uneven Polyethylene inflation, how vertical streaks indicate contamination in the extrusion die, how wall bubbles arise from trapped gases or moisture, how orange peel surfaces result from uneven crystallization rates, how bottom wrinkles form due to overheating or mistimed pre-blowing, and how finished trim defects create jagged sealing surfaces that compromise functionality. Understanding these defects, their appearance, causes, and prevention is essential for maintaining the high-quality standards we discussed in the previous segment. Each defect represents a deviation from optimal processing, and each provides diagnostic information that skilled technicians and engineers use to continuously refine and improve the manufacturing process, ensuring that the vast majority of containers meet the stringent quality requirements for food packaging. As our exploration of high-density polyethylene containers continues, we now turn our attention to one of the most demanding phases in the life cycle of certain HDPE products: the sterilization process. While we have discussed HDPE's thermal stability and its ability to withstand elevated temperatures, we have not yet fully examined the complex interplay of heat, pressure, and mechanical stress that occurs when filled containers undergo retort sterilization. This process, essential for creating shelf-stable dairy and food products, subjects HDPE containers to conditions that push the material to the limits of its capabilities. Tonight, we delve into the challenges of sterilization, exploring how pressure differentials develop, how they affect container integrity, and how manufacturers have developed sophisticated strategies to minimize damage and maintain quality during this critical phase of production. The sterilization process subjects sealed containers to extreme conditions. During sterilization, internal bottle pressure can exceed 5 bar, a level of pressure that creates substantial stress on the container walls and structure. To understand this, we must first appreciate what 5 bar represents. 1 bar is approximately equal to atmospheric pressure at sea level, so 5 bar represents 5 times normal atmospheric pressure, or about 73 pounds per square inch. This internal pressure develops because the container is filled with liquid and sealed, and then the entire assembly is heated to sterilization temperatures, often 120 degrees Celsius or higher. As the liquid inside heats, it expands, and any air space in the container also expands according to the gas laws, increasing pressure. Additionally, if the heating is rapid or if the liquid contains dissolved gases, these gases may come out of solution, further increasing pressure. The HDPE container walls must contain this pressure without rupturing, a demanding requirement given that the walls are typically only a few millimeters thick. The polymer chains, through their intermolecular forces and the structural integrity provided by crystalline regions, must resist the outward force that the internal pressure exerts on every square centimeter of the container surface. The tensile strength of HDPE becomes critically important during this phase. The material must stretch slightly to accommodate the pressure without yielding or tearing. The container may visibly swell during sterilization, expanding in diameter and height as the walls bulge outward, but it must return to its original dimensions upon cooling without having suffered permanent deformation or damage. To prevent containers from bursting during sterilization, the retort vessel itself is pressurized. External retort pressure often starts near 2 bar and is carefully controlled throughout the sterilization cycle. The retort is a large pressure vessel, essentially an industrial autoclave, that can hold hundreds or thousands of containers. Steam, or a mixture of steam and air, is introduced to heat the containers and create the pressurized environment. The external pressure serves a critical function. It provides support to the container walls, counteracting some of the internal pressure and reducing the net stress on the HDPE structure. If containers were sterilized in an unpressurized environment, the internal pressure would be unopposed and would almost certainly cause the containers to rupture or deform severely. By applying external pressure, the effective stress on the container walls is the difference between internal and external pressure rather than the full internal pressure. Starting the external pressure near 2 bar, while internal pressure may ultimately reach 5 bar, means there is initially a 3 bar pressure differential, with the inside higher than the outside. This differential, while still substantial, is manageable for HDPE containers if properly designed and if the sterilization cycle is carefully controlled. The external pressure is typically ramped up as the internal pressure increases, attempting to maintain a relatively constant pressure differential throughout the heating phase. However, achieving perfect balance between internal and external pressure throughout the sterilization cycle is extraordinarily difficult. Pressure imbalance causes bottles to expand and contact each other, creating one of the primary challenges in retort processing. The bottles enter the retort arranged in baskets or crates, spaced to allow steam circulation, but positioned relatively close together for efficient use of the retort volume. As sterilization begins and temperatures rise, the pressure inside each bottle increases, but not necessarily at exactly the same rate as the external pressure. If internal pressure rises faster than external pressure, the bottles swell outward. Given that they start out near each other, this swelling brings them into contact. Once in contact, the bottles exert forces on each other as they continue to expand or as the pressure differential fluctuates. These forces can dent the bottles, creating permanent deformations in the walls. The situation is complicated by variability between bottles. Differences in fill level, air space, wall thickness, or exact positioning in the basket mean that each bottle experiences slightly different pressure histories. Some bottles may expand more than others, and these expanding bottles may press against their neighbors that are expanding less. The molecular structure of HDPE allows the material to deform plastically under sustained pressure and temperature. When bottles are pressed together while the polymer is hot and softened, the chains can flow slightly, creating permanent dents that remain even after cooling and pressure release. The frequency of this damage can be significant in operations that have not optimized their processes. Denting can affect over 2% of production without optimization, representing a substantial loss in facilities producing millions of containers monthly. 2% may not sound like a large number, but in a production environment running at high volume, it translates to thousands or tens of thousands of damaged containers each day. Each dented container represents wasted material, energy, and filled product. The container cannot be sold. The product inside may need to be discarded, and resources have been consumed in manufacturing, filling, and sterilizing a defective unit. Beyond the direct material losses, dented containers disrupt production flow, requiring sorting and disposal, and they may cause equipment jams or other issues downstream. The economic impact is substantial, making dent reduction a high priority for manufacturers. The fact that denting rates can be so high without optimization also indicates how challenging the retort sterilization process is. Achieving the right balance of temperatures, pressures, timing, and bottle design requires sophisticated understanding and careful control. Fortunately, research and engineering have identified effective strategies for mitigation. Optimized retort pressure significantly reduces dented containers, with studies showing reductions from over 2% down to well under 1% or even to negligible levels. The optimization involves carefully profiling the external pressure throughout the sterilization cycle to match as closely as possible the internal pressure development in the bottles. This requires understanding the heat transfer into the bottles, the thermal expansion characteristics of the specific product being sterilized, the response of the particular HDPE formulation being used, and the dynamics of pressure equilibration in the retort. Advanced retort systems incorporate multiple pressure and temperature sensors, programmable pressure control valves, and sophisticated software that adjusts external pressure in real time based on measured conditions. The pressure profile might include a rapid initial pressurization to get ahead of internal pressure development, a holding period at constant pressure during the main heating phase, and a controlled depressurization synchronized with cooling to avoid creating reverse pressure differentials that could cause bottles to collapse. Some systems use air overpressure in addition to steam, allowing more precise control of pressure independent of temperature. The investment in optimized pressure control systems pays for itself rapidly through reduced losses. The economic benefit of these improvements is substantial. Pressure control improvements save tens of thousands of bottles monthly in typical production facilities. A facility producing 1 million bottles per month that reduces dent rates from 2.5% to 0.5% saves 20,000 bottles monthly. At typical costs including material, filling, energy, and labor, each saved bottle represents several cents of value, translating to thousands of dollars in monthly savings from a single improvement. Multiplied across multiple production lines or facilities, the savings become significant. Beyond the direct cost savings, reducing defects improves customer satisfaction, reduces waste and environmental impact, and allows production capacity to be used more effectively since less time is spent sorting and managing defects. The engineering expertise required to achieve these improvements, process engineers, materials scientists, equipment specialists, represents an investment that delivers ongoing returns through improved yield and quality. Bottle design and retort loading also play critical roles in defect prevention. Bottle spacing within retort baskets influences deformation rates significantly. If bottles are packed too tightly, even small amounts of expansion bring them into contact, and the contact forces have nowhere to dissipate. The bottles simply press harder against each other. If bottles are spaced too far apart, retort capacity is wasted, reducing efficiency. The optimal spacing allows for the expected expansion during sterilization while minimizing contact. This spacing might be just a few millimeters per bottle, requiring precise basket design. The baskets themselves must be rigid enough not to deform under the forces involved, but must also allow free steam circulation to ensure uniform heating. Some basket designs incorporate cellular structures that cradle each bottle, preventing it from moving laterally into neighbors while still allowing vertical expansion. Others use specific patterns of dividers or supports. The material of the baskets must withstand repeated sterilization cycles without corroding or degrading. Additionally, the orientation of bottles matters. Bottles should be upright and stable, as tilted bottles may contact neighbors at different points and create concentrated stress. Loading procedures must be carefully followed, with operators trained to position bottles correctly and to ensure baskets are not overloaded. The containers are sealed with closures that must also withstand the sterilization process. Aluminum lids use multi-layer structures for secure sealing, combining different materials to achieve the necessary combination of properties. A typical aluminum lid might consist of an aluminum foil layer for barrier properties and formability, a polymer heat seal layer that fuses to the HDPE bottle rim, and possibly additional layers for strength or to provide specific barrier characteristics against oxygen, moisture, or light. The multi-layer structure is created through lamination processes that bond the layers together with adhesives or through co-extrusion. The aluminum provides excellent barrier properties, preventing oxygen transmission that could spoil the product, and also provides stiffness that helps the lid maintain its shape. The polymer heat seal layer, often a polyethylene or modified polyethylene compatible with HDPE, softens when heated and bonds to the bottle rim, creating a hermetic seal. During sterilization, this seal must withstand both the elevated temperature and the pressure differential without failing. The lid may also incorporate tamper evidence features, or easy open tabs. The complexity of these multi-layer lids reflects the demanding requirements of the sterilized packaging application. During the sterilization process, mechanical interactions between components can cause damage. Friction during sterilization can damage lid surfaces, creating scratches, scuffs, or displaced material that may compromise the seal or the appearance. As bottles expand and shift during heating, the lids may rub against basket structures, against other bottles' lids, or against the sides of the retort. The combination of pressure, heat, and mechanical motion creates conditions conducive to friction and wear. Damaged lid surfaces may develop leaks, particularly if scratches penetrate through protective coatings or barrier layers. Even minor surface damage can be problematic, as it may create pathways for oxygen ingress or moisture transmission, compromising the shelf stability of the product. Additionally, damaged lids are cosmetically unacceptable, affecting consumer perception of product quality. Minimizing friction damage requires attention to basket design to avoid sharp edges or rough surfaces, proper bottle spacing to reduce movement and contact, and possibly the use of lubricants or coatings on basket components. The retort cycle itself can be optimized to minimize agitation and movement of containers during the critical high-temperature phases. Despite all optimization efforts, some level of defects persists in any manufacturing operation. Dented bottles represent the most common production defect in retort-sterilized HDPE container operations, surpassing other issues like leaks, finish defects, or contamination. This prevalence reflects the fundamental challenges of the sterilization process, the extreme conditions, the complex interplay of variables, and the inherent variability in materials and processes. Even with optimized pressure control, ideal spacing, and careful handling, occasional dents occur due to factors like unusual bottle-to-bottle variations, equipment transients, or random contact events. The persistence of denting as the primary defect also indicates that other defect categories have been effectively addressed through decades of process improvement. Leak rates are extremely low due to excellent sealing technology. Finish defects are minimized through precision molding and trimming. Contamination is prevented through clean manufacturing practices. Denting remains the frontier because it involves dynamic mechanical interactions during an extreme thermal process, making it particularly challenging to eliminate completely. Continuous improvement efforts focus on this defect category because of its prevalence and impact. As we conclude this 8th segment, we have explored the demanding world of retort sterilization for HDPE containers and the pressure-related challenges that arise during this process. We have examined how internal bottle pressure can exceed 5 bar during sterilization, creating substantial stress on container walls, how external retort pressure near 2 bar provides partial support but cannot fully balance internal pressure, how pressure imbalances cause bottles to expand and contact each other, how denting can affect over 2% of production in non-optimized operations, how optimized retort pressure control significantly reduces dented containers, how these improvements save tens of thousands of bottles monthly with corresponding economic benefits, how bottle spacing within retort baskets influences deformation rates and must be carefully designed, how aluminum lids use multi-layer structures to achieve secure sealing under extreme conditions, how friction during sterilization can damage lid surfaces and compromise performance, and how dented bottles represent the most common production defect in this application. These challenges highlight the demanding nature of sterilized packaging and demonstrate how material science, process engineering, and equipment design must work together to achieve acceptable quality levels, pushing HDPE to the limits of its capabilities while still producing reliable containers for shelf-stable products. As we approach the later stages of our exploration of high-density polyethylene, we must turn our attention to a sobering reality: the environmental persistence and ultimate fate of this remarkable material. The very properties that make HDPE so valuable in service, its chemical resistance, its structural stability, its resistance to moisture and biological attack, also make it extraordinarily persistent in the environment once its useful life has ended. Tonight, we examine the long-term behavior of HDPE, its resistance to natural degradation processes, the mechanisms by which it can deteriorate under specific conditions, the challenges it presents for disposal and recycling, and the safety considerations that arise throughout its life cycle. This segment brings us face to face with the environmental implications of our reliance on synthetic polymers and the importance of responsible end-of-life management. The fundamental chemical structure of HDPE determines its environmental persistence. HDPE's carbon-carbon backbone resists biodegradation for centuries, remaining essentially unchanged in most natural environments for time periods that span multiple human generations. Biodegradation is the process by which living organisms, primarily bacteria and fungi, break down organic materials into simpler compounds, eventually returning them to the natural cycles of carbon, hydrogen, and other elements. Most natural organic materials, wood, paper, food waste, natural fibers, biodegrade relatively readily because microorganisms have evolved enzymes capable of cleaving the chemical bonds in these materials. However, the carbon-carbon bonds that form the backbone of HDPE are extraordinarily stable. These bonds, with their strong covalent character and shielding by hydrogen atoms, present no reactive sites that the enzymes produced by common microorganisms can attack. Furthermore, HDPE's hydrophobic nature and lack of functional groups that microorganisms could recognize or metabolize mean that bacteria and fungi simply do not perceive it as a potential food source. An HDPE milk jug discarded in a landfill or in the natural environment will remain largely intact for hundreds of years, possibly longer. The polymer chains do not spontaneously break down, do not dissolve in water, do not react with soil components. This persistence is both a testament to the stability of the material and a significant environmental challenge, as discarded HDPE accumulates in landfills and, unfortunately, in natural environments where it contributes to plastic pollution. While HDPE resists biological degradation, it is not completely immune to environmental degradation through other mechanisms. Prolonged UV exposure causes embrittlement and discoloration, gradually degrading the mechanical properties that make HDPE useful. Ultraviolet radiation from sunlight carries enough energy to break certain chemical bonds, particularly in the presence of oxygen. When UV photons strike HDPE, they can excite electrons in the polymer structure, occasionally providing enough energy to cleave a carbon-hydrogen bond or, less commonly, a carbon-carbon bond along the backbone. This photochemical degradation initiates a cascade of reactions. Once a bond is broken, free radicals form, highly reactive molecular fragments with unpaired electrons. These free radicals can abstract hydrogen atoms from neighboring chains, propagating the damage, or they can react with oxygen in the air, creating peroxy radicals and other reactive species. Over time, these reactions lead to chain scission, where long polymer chains are broken into shorter segments, reducing molecular weight. They also lead to cross-linking, where chains bond together at points of radical formation. The combination of chain scission and cross-linking changes the material's properties dramatically. The HDPE becomes increasingly brittle, losing the ductility and impact resistance that characterize fresh material. Surface cracking develops, and the material may become chalky or powdery. Discoloration occurs as the chemical changes create chromophoric groups, molecular structures that absorb visible light, causing yellowing or darkening. HDPE containing white pigment may fade or yellow. Material that was once strong and flexible becomes weak and brittle, crumbling under stresses that it would have easily withstood when new. The chemical mechanism of UV degradation involves specific reactions at the molecular level. UV oxidation forms carbonyl groups on polymer surfaces, creating chemical functionalities that did not exist in the original material. Carbonyl groups consist of a carbon atom double bonded to an oxygen atom, and they form when free radicals created by UV radiation react with atmospheric oxygen and subsequently abstract hydrogen from the polymer or rearrange into stable structures. The presence of carbonyl groups can be detected through infrared spectroscopy, which reveals characteristic absorption bands that serve as markers of oxidative degradation. These carbonyl groups represent weak points in the polymer structure and sites where further degradation can occur. They also alter the surface properties of the HDPE, potentially making it more hydrophilic and changing how it interacts with the environment. The formation of carbonyl groups progresses from the surface inward, as UV radiation penetrates only a limited depth into the polymer. Thus, a weathered HDPE container may have a degraded, brittle surface layer, while the interior material remains relatively unaffected. This surface degradation is why outdoor HDPE applications often incorporate UV stabilizers, additives that absorb UV radiation or quench free radicals, protecting the polymer from photodegradation and extending service life. Given HDPE's resistance to biodegradation, some have explored whether composting conditions might accelerate breakdown. However, microbial composting removes only a small fraction of material mass from HDPE, even under controlled conditions designed to optimize microbial activity. Composting involves creating conditions of elevated temperature, moisture, and oxygen availability that promote rapid microbial growth and organic matter decomposition. While these conditions are highly effective for breaking down food scraps, yard waste, and other natural materials, they have minimal impact on HDPE. Studies that have subjected HDPE to industrial composting conditions for weeks or months typically find mass losses of only a few % at most, and even this small loss may represent leaching of additives or physical abrasion rather than true biodegradation of the polymer chains. Some microorganisms can colonize HDPE surfaces, creating biofilms, but they are not actually consuming the polymer. They are living on the surface and metabolizing trace organic compounds, contaminants, or additives present in the material. There has been research into specialized bacteria and fungi that show some ability to degrade polyethylene, but these organisms work extremely slowly and are not present in typical composting environments. The reality is that composting is not a viable disposal method for HDPE, and HDPE contamination in compost feedstock is problematic because it persists through the composting process and contaminates the finished compost product. While HDPE resists degradation under most conditions, certain environments can trigger specific failure modes. Chemical exposure can trigger environmental stress cracking, a phenomenon where the combination of mechanical stress and chemical attack causes cracks to initiate and propagate through the material, even though neither the stress nor the chemical alone would cause failure. Environmental stress cracking occurs when certain chemicals, particularly surfactants, oils, or other organic liquids, penetrate into regions of high stress within the HDPE structure. These chemicals may not dissolve or chemically react with the polymer in the traditional sense, but they reduce the cohesive forces between polymer chains, effectively lubricating the chains and allowing them to slide past each other more easily. In regions where the material is under tensile stress, perhaps from internal pressure in a container, from residual molding stresses, or from applied loads. This reduction in intermolecular forces allows microscopic cracks to form and grow. Once initiated, these cracks propagate through the stressed regions, following paths between crystalline domains and through the amorphous regions where chain entanglement is disrupted by the penetrating chemical. Environmental stress cracking can cause catastrophic failure of containers that appeared perfectly sound, with ruptures occurring suddenly and without warning. Certain chemicals are particularly aggressive in promoting this type of cracking, including some detergents, essential oils, and petroleum distillates. HDPE formulations and product designs must consider environmental stress cracking resistance for applications where such chemical exposure is likely. Thermal abuse of HDPE during processing or disposal can create additional concerns. Overheating HDPE releases volatile organic compounds that may pose health and environmental concerns. When HDPE is heated well above its normal processing temperatures, into the range of 300 to 400 degrees Celsius or higher, thermal degradation accelerates dramatically. The polymer chains undergo pyrolysis, breaking down into smaller fragments that can volatilize and escape into the air. These volatile organic compounds include a complex mixture of hydrocarbons ranging from small molecules like methane and ethylene to longer-chain alkanes, alkenes, and aromatic compounds. Some of these compounds have characteristic odors, the smell of burning plastic that most people recognize. Others may be irritating to the respiratory system or have other health effects. While HDPE itself consists only of carbon and hydrogen, and thus produces relatively benign combustion products compared to polymers containing chlorine or other elements, the release of VOCs during overheating is still undesirable from both a health and environmental perspective. In manufacturing, maintaining proper processing temperatures and avoiding overheating is important for both product quality and workplace air quality. In disposal, uncontrolled burning of HDPE waste creates air pollution. The manufacturing of HDPE itself involves materials and conditions that require careful safety management. Certain polymerization catalysts pose occupational hazards requiring careful handling protocols and protective equipment. The Ziegler-Natta catalysts we discussed earlier, based on titanium compounds and aluminum alkyls, are pyrophoric. They can spontaneously ignite when exposed to air. They are also reactive with moisture and can cause chemical burns. Workers handling these catalysts must use inert atmospheres, specialized equipment, and personal protective gear including respirators, gloves, and protective clothing. The chromium-based catalysts also present hazards, as hexavalent chromium compounds are known carcinogens and toxic substances. While the chromium in properly formulated catalysts is in different oxidation states and bound in ways that reduce hazard, care must be taken in catalyst preparation and handling. Metallocene catalysts, while generally less hazardous than earlier catalyst types, still require careful handling. The polymerization process itself involves pressurized systems containing flammable ethylene gas, creating explosion hazards that must be managed through proper equipment design, monitoring, and safety systems. The chemical industry has developed extensive protocols for safe handling of these materials, but the inherent hazards emphasize that HDPE production, while creating a safe end product, involves sophisticated chemical processes that demand expertise and caution. HDPE's behavior in fire is characterized by its flammability rating. HDPE has a UL94 HB flammability rating, indicating that it is a slow-burning material under standard testing conditions. The UL94 standard, developed by Underwriters Laboratories, classifies plastic materials according to their burning behavior in various orientations and conditions. The HB rating, horizontal burn, is the lowest classification in the standard and indicates that when a horizontal specimen is ignited, it burns at a rate no faster than a specified maximum. HDP will ignite when exposed to sufficient heat or flame, and once ignited, it will continue to burn while producing molten drips that can themselves ignite other materials. The material burns with a characteristic blue flame with a yellow tip, producing the smell of burning wax or paraffin. Unlike some polymers that self-extinguish when the ignition source is removed, HDP typically continues burning until consumed or until oxygen is exhausted. This flammability characteristic means that HDP containers should not be used near open flames or high heat sources, and that accumulated HDP waste represents a fire load in storage and disposal facilities. Fire retardant additives can be incorporated into HDP formulations for applications requiring improved fire resistance, though these additives add cost and may affect other properties. One potential end-of-life pathway for HDP is energy recovery through combustion. Combustion recovers most of HDP's stored energy, as the carbon-hydrogen bonds in the polymer release energy when oxidized to carbon dioxide and water. HDP has a heat of combustion similar to that of petroleum products, approximately 46 megajoules per kilogram, making it a reasonable fuel for waste-to-energy facilities. When burned in controlled conditions with adequate air and high temperatures, HDP combusts relatively cleanly, producing primarily carbon dioxide and water vapor. The energy released can be captured as heat for industrial processes or converted to electricity through steam turbines. This energy recovery represents a form of recycling, as it displaces fossil fuels that would otherwise be burned for energy. However, combustion is generally considered inferior to material recycling from a sustainability perspective, as it consumes the polymer rather than preserving the molecular structure for continued use. Combustion also produces carbon dioxide emissions, contributing to greenhouse gas concentrations in the atmosphere, even though these emissions represent carbon that was originally extracted from fossil sources and would eventually return to the atmosphere through degradation or combustion regardless. Finally, we must recognize a critical limitation regarding recycled HDP. Burned HDP cannot return to food-grade use, and more broadly, HDP that has been through certain degradation or contamination pathways faces restrictions on reuse in food contact applications. Combustion obviously destroys the polymer entirely, but the statement also reflects a broader principle in food packaging. Materials that have been exposed to unknown contaminants, or that have undergone degradation, cannot be certified as safe for direct food contact. Even mechanically recycled HDP faces regulatory scrutiny for food contact applications. Post-consumer HDP that has been collected, cleaned, and reprocessed may contain trace contaminants that are difficult to completely remove. Residues from previous contents, environmental contaminants from storage, degradation products from weathering or thermal history. Regulatory agencies require extensive testing and often limit the use of post-consumer recycled content in food packaging to certain percentages, or require barrier layers of virgin material between recycled material and food. Post-industrial regrind, which comes from manufacturing operations and has known history, faces fewer restrictions, but still requires validation. The inability to freely recycle all HDP back into food packaging creates challenges for closing the loop on milk jugs and similar containers, requiring development of non-food applications for recycled material, or investment in advanced recycling technologies that can restore material to virgin equivalent purity. As we conclude this 9th segment, we have confronted the environmental realities of high-density polyethylene, examining how the material's carbon-carbon backbone resists biodegradation for centuries in natural environments, how prolonged UV exposure causes embrittlement and discoloration through photochemical degradation, how UV oxidation forms carbonyl groups that mark and accelerate degradation, how microbial composting removes only minimal mass from HDP and cannot serve as a disposal method, how chemical exposure can trigger environmental stress cracking that causes unexpected failure, how overheating releases volatile organic compounds with health and environmental implications, how certain polymerization catalysts pose occupational hazards requiring protective protocols, how HDPE's UL94HB flammability rating indicates it is combustible and requires appropriate safety precautions, how combustion can recover most of the material's stored energy as an end-of-life option, and how burned or contaminated HDP cannot return to food-grade applications. These environmental and safety considerations remind us that while HDP serves us extraordinarily well during its use phase, responsible stewardship requires careful attention to manufacturing safety, end-of-life management, and the development of sustainable circular economy approaches that minimize environmental impact. As we arrive at the final segment of our journey through the molecular world of high-density polyethylene, we turn our attention to perhaps the most hopeful aspect of this material's story: its capacity for rebirth through recycling and reprocessing. While our previous segment examined the environmental challenges posed by HDP's persistence, we now explore how this durable material can be recovered, transformed, and given new life in subsequent applications. The recycling of HDP represents both a practical response to environmental concerns and a fascinating study in materials science, revealing how polymer properties evolve through repeated processing and how innovative approaches can create value from what would otherwise be waste. Tonight, we conclude our exploration by examining the technical realities of HDP recycling, the challenges and opportunities it presents, and the pathways through which discarded milk jugs can become the raw material for entirely new products. The recycling process subjects HDP to conditions that inevitably affect its molecular structure. Recycled HDP chains shorten after multiple processing cycles, a phenomenon that reflects the accumulated thermal and mechanical stress experienced during collection, cleaning, melting, and reprocessing. Each time HDP is melted, some degree of chain scission occurs. At the elevated temperatures required for processing, polymer chains have increased molecular motion and energy, making them more susceptible to breaking. Oxidative degradation accelerates this process if oxygen is present, as it often is during recycling operations that may not have the controlled atmospheres of virgin polymer production. Mechanical shearing forces in extruders and other processing equipment also contribute to chain breakage, as the intense mixing and pumping action can literally tear chains apart. After a single recycling pass, the molecular weight distribution shifts toward lower values. The longest chains are most susceptible to breakage, so they are selectively shortened. After multiple recycling cycles, the average molecular weight may decrease substantially. This shortening of chains has direct consequences for mechanical properties. Shorter chains mean fewer entanglements between molecules, reduced intermolecular forces across the bulk material, and diminished ability to distribute stress. The material becomes progressively weaker and more brittle with each recycling cycle, placing practical limits on how many times HDP can be recycled before its properties degrade below useful levels. The degradation of properties through recycling can be quantified through testing. Impact strength drops by 10 to 20% after repeated recycling, reflecting the reduced molecular weight and the accumulated damage from thermal and oxidative degradation. Impact strength, as we discussed in earlier segments, measures the material's ability to absorb sudden shocks without fracturing. This property depends critically on having long polymer chains that can dissipate impact energy through chain stretching, disentanglement, and movement within the amorphous regions. When chains are shortened through recycling, these energy-absorbing mechanisms become less effective. The material has less capacity to deform before failure, and cracks can propagate more easily through the structure. A 10 to 20% reduction in impact strength is significant. It may represent the difference between a container that survives being dropped and one that cracks or fails. For this reason, recycled HDPE is often not used alone in applications requiring maximum impact resistance, but is instead blended with virgin material to restore properties, or it is directed toward applications where somewhat reduced mechanical performance is acceptable. The degradation is not linear. The first recycling cycle typically causes the most significant property loss, with subsequent cycles showing progressively smaller incremental degradation as the most vulnerable long chains have already been broken, and what remains is a more stable population of shorter chains. Maintaining the quality of recycled HDPE requires careful management of the recycling stream to prevent contamination. Optical sorting prevents contamination in recycled resin streams by automatically identifying and separating different types of plastics based on their optical properties. Modern recycling facilities employ sophisticated sorting systems that use infrared spectroscopy, visible light cameras, and artificial intelligence to examine each piece of plastic waste as it passes on a conveyor belt at high speed. Different polymers have characteristic absorption and reflection spectra in the near-infrared range, allowing the system to distinguish HDPE from PET, PVC, polypropylene, and other plastics. When a piece is identified as HDPE, precisely timed air jets blasted off the main conveyor into a collection stream. This automated sorting is far more accurate and rapid than manual sorting, achieving purity levels above 95% and processing rates of many tons per hour. Preventing contamination is crucial because even small amounts of incompatible polymers can degrade the properties of recycled HDPE. PVC contamination is particularly problematic as it can release corrosive hydrogen chloride during processing and create defects in the recycled resin. Optical sorting also typically separates HDPE by color, creating streams of natural, white, colored, and mixed material, as color affects the potential applications for the recycled resin. The physical characteristics of the HDPE being recycled influence processing efficiency. Translucent HDPE melts more uniformly than pigmented variants, a difference that arises from how heat transfers through the material during melting. Translucent or natural HDPE, containing no pigments, allows some infrared radiation to penetrate into the material, creating more uniform heating throughout each piece or pellet. Pigmented HDPE, particularly dark colors, absorbs radiation at the surface, creating steeper temperature gradients between surface and interior. These temperature gradients mean that when pigmented HDPE is being melted in an extruder or other processing equipment, the surface material may be fully molten while interior regions remain partly solid, requiring more residence time and mixing to achieve a uniform melt. The more uniform melting of translucent material allows for faster processing and potentially less thermal degradation, since the average temperature can be lower while still achieving complete melting. This is one reason why natural or translucent HDPE often commands higher prices in recycling markets. It is easier to process and more versatile for reuse, as it can be colored to any desired shade in subsequent applications, whereas pigmented recycled material is limited to uses where its existing color is acceptable or where it will be further pigmented. Recycled HDPE can be transformed into solid forms quite different from the hollow containers it originated from. Recycled jugs can be compression molded into dense blocks or sheets, creating materials suitable for entirely new applications. Compression molding involves placing ground or flaked recycled HDPE into a heated mold cavity and applying pressure to force the material into the mold shape. As heat and pressure are applied, the HDP softens and flows, fusing together into a solid mass. Unlike blow molding, which creates hollow shapes, compression molding creates solid parts with uniform cross-sections. The density of compression molded recycled HDP is typically higher than that of virgin HDP because the applied pressure forces out air voids and compacts the material. These dense blocks can be machined into various products, cutting boards, construction materials, outdoor furniture components, drainage products, and countless other applications. The compression molding process can accommodate material with somewhat degraded properties because the solid cross-section provides structural support that doesn't rely solely on tensile strength in thin walls. Additionally, compression molding can handle mixed or contaminated recycled streams that would be problematic for blow molding or injection molding. The thermal processing of recycled HDP requires carefully controlled temperatures. Heating to 250 to 300 degrees Fahrenheit enables chain flow for reuse while minimizing further degradation. 250 degrees Fahrenheit is approximately 121 degrees Celsius, just below HDP's typical melting point, while 300 degrees Fahrenheit is approximately 149 degrees Celsius, comfortably above the melting point, but not excessively high. This temperature range ensures that the polymer chains have sufficient thermal energy and mobility to flow and fuse together, creating homogeneous recycled material, while avoiding the accelerated degradation that occurs at higher temperatures. The specific optimal temperature depends on the molecular weight of the recycled material. Degraded material with shorter chains will flow at lower temperatures than virgin material with longer chains. Processing equipment for recycled HDP typically includes multiple temperature zones that gradually heat the material as it moves through the system, allowing for efficient melting without thermal shock or degradation. Residence time is also controlled. The material should spend only as long as necessary in the heated zones to achieve complete melting and homogenization, with minimal additional time that would allow degradation to progress. Innovative approaches to recycled HDP can actually enhance certain properties beyond those of the virgin material. Upcycled HDP composites can exceed 120 degrees Celsius heat resistance through the incorporation of fillers, reinforcements, or specialized additives. By blending recycled HDP with materials like wood fibers, glass fibers, mineral fillers, or high-temperature polymers, manufacturers can create composite materials that retain the processability and basic characteristics of HDP, while gaining enhanced heat resistance, stiffness, or dimensional stability. The composite materials might use recycled HDP as the matrix, providing cohesion and processability, while the added components provide reinforcement and thermal stability. Wood plastic composites, which blend recycled HDP with wood flour or fibers, have become a major market for recycled material, producing decking, fencing, and outdoor furniture that resists rot, insects, and weathering while offering appearance similar to wood. These composites can tolerate higher service temperatures than pure HDP and have greater rigidity, making them suitable for structural applications. The term upcycling reflects that these processes add value to the recycled material rather than simply maintaining or accepting reduced value, transforming waste into premium products. Addressing the property degradation that occurs during recycling can involve strategic use of additives. Copolymer additives improve toughness in recycled blends by introducing polymer chains with different structures that enhance impact resistance and flexibility. These copolymers might be polyethylene with controlled branching, ethylene vinyl acetate copolymers, or other materials that are compatible with HDP but provide enhanced toughness. When blended into recycled HDP, these additives create a material system where the recycled HDP provides the bulk properties and cost advantages, while the copolymer additives restore or enhance toughness that was lost during recycling. The copolymers may work by improving stress distribution, enhancing energy absorption in the amorphous regions, or creating a more robust network of entanglements between chains. Relatively small percentages of copolymer additives, perhaps 5 to 15% by weight, can significantly improve the performance of recycled HDPE blends, making them suitable for demanding applications. This approach is more cost-effective than using pure virgin HDPE, while achieving performance that meets application requirements. Beyond the environmental benefits of waste reduction, recycling offers tangible energy advantages. Recycling reduces energy consumption per jug by up to 30% compared to manufacturing from virgin resin. This energy savings arises because the most energy-intensive step in HDPE production, the cracking of petroleum or natural gas to produce ethylene and the subsequent polymerization, is eliminated when using recycled material. The energy required to collect, sort, clean, grind, melt, and reprocess recycled HDPE is substantially less than the energy required to produce virgin polymer from raw materials. A 30% reduction in energy consumption translates directly to reduced carbon emissions, reduced air pollution from power generation, and reduced consumption of fossil fuels. Over the billions of HDPE containers produced annually, this energy savings becomes significant at a global scale. The economic benefits are also substantial. Recycled HDPE typically costs less than virgin material, providing cost savings for manufacturers while delivering environmental benefits. These combined economic and environmental advantages create strong incentives for increasing recycling rates and expanding markets for recycled HDPE. The ultimate vision for HDPE recycling extends beyond simply making more bottles. HDPE milk jugs can be transformed into new industrial materials with entirely different forms and functions, closing loops in unexpected ways. That milk jug that served its purpose holding a gallon of dairy might be reborn as a park bench that will serve for decades, as drainage pipe that manages stormwater, as synthetic lumber for a deck or dock, as a protective case for equipment, as pellets for injection molding new consumer products, or as any of thousands of other applications. The versatility of recycled HDPE as a raw material means that the molecular chains synthesized decades ago for one purpose can serve many subsequent purposes, each time being collected, reprocessed, and reformed into new shapes. This is the promise of a circular economy for polymers. Not that materials will be recycled infinitely without degradation, which thermodynamics and chemistry make impossible, but that materials will serve multiple useful lives before their properties degrade beyond utility, and that even then, energy recovery or advanced recycling technologies might extract final value. The milk jug becomes a symbol of this circularity, a humble container that demonstrates both the remarkable properties that molecular engineering can achieve and the responsibility we bear to steward these materials wisely through all phases of their existence. As we bring our 10-segment journey through the world of high-density polyethylene to a close, we reflect on the remarkable scope of what we have explored. From the molecular weight and crystallinity that define HDPE's fundamental character, through the mechanical properties that enable its function, the thermal behavior that governs its processing, the manufacturing precision that transforms pellets into containers, the quality systems that ensure reliability, the defects that reveal process sensitivities, the sterilization challenges that push materials to their limits, the environmental persistence that demands responsible management, and finally to the recycling technologies that offer pathways to sustainability. We have witnessed how chemistry, physics, engineering, and environmental stewardship interweave in the story of a single material. The HDPE milk jug, so familiar and so easily overlooked, embodies scientific knowledge accumulated over decades, represents industrial capabilities of extraordinary sophistication, and carries within its molecular structure both the promise of human ingenuity and the challenge of environmental responsibility. May this exploration bring new appreciation for the materials that serve us daily and inspire thoughtful consideration of how we might use and steward them more wisely.